You are entering a world that looks and feels surprisingly close to home. The light here is not yellow like sunlight on Earth, but deep red-orange, and it paints everything in shades of rust and amber that feel alien, yet warm. Your spacecraft descends through a thin atmosphere towards solid ground, instruments confirming what your eyes already tell you, that this world is different from home. The landscape below shows rocky terrain, reddish-brown stone extending toward a horizon that curves more sharply than Earth's horizon would at the same altitude. You are landing on TRAPPIST-1e, the most Earth-like planet in a system of 7 worlds, 40 light-years from home. The star hangs in the sky above you. Smaller than our sun appears from Earth, but still prominent, a dull red disk providing steady warmth. This is TRAPPIST-1, an ultra-cool red dwarf, barely massive enough to be a star, yet sustaining 7 Earth-sized planets in tight orbits. The spacecraft touches down gently in reduced gravity, slightly less than Earth's pull, and the engines quiet to silence as the landing completes. Through the viewport you see stone and dust, and a sky that shifts from deep salmon near the horizon to darker, peachy orange overhead. You are listening to the Drowsy Astronaut, and tonight we travel together through the TRAPPIST-1 system, visiting all 7 worlds, one by one. We will move slowly through each planet, taking time to see what exists, to experience what it would feel like to stand there. I already know you're listening from somewhere here on Earth tonight, and I'd love to know where. Feel free to share where you are in the comments. And if you'd like to join us for more journeys through the cosmos, a like or subscription is always appreciated. Now we step outside onto TRAPPIST-1e, beginning our exploration of this remarkable family of worlds, orbiting a small red star. The hatch opens, and you step down onto the surface, your boots touching reddish stone that has never known rain or wind as Earth understands them. The gravity feels lighter, your movement slightly easier, each step requiring less effort than the same motion would require back home on Earth. The temperature reads comfortable on your suit display, warm like a pleasant spring afternoon, neither too hot nor too cold for extended exploration here. This world sits in the middle of the habitable zone, the region around the star, where temperatures could allow liquid water to exist on the surface. Looking up, you notice something extraordinary that makes this place unlike anywhere in our solar system, something that justifies the journey of 40 light-years. Other planets hang in the sky above you, not as tiny points of light like Venus or Mars appear from Earth, but as visible disks. TRAPPIST-1f, the next planet outward from the star, appears larger than the Moon looks from Earth's surface, showing clear phases like a crescent. You can see it clearly even in the daylight, under this red sun, a sibling world hanging in the peachy sky, just there, above the horizon. Turning slowly in place, you scan the sky and find more planets scattered across the view, some showing as crescents, some as half-lit disks. TRAPPIST-1d sits closer to the star from your vantage point, appearing smaller but still clearly a disk rather than a point. The innermost planets, TRAPPIST-1b and c, are harder to see against the star's glare, but the outer worlds are unmistakable. You are standing on one of 7 Earth-sized worlds, and from here you can see 6 others with your own eyes. No telescope needed. The landscape around you consists of dark reddish-brown rock, rough and uneven, with scattered smaller stones covering much of the visible ground surface. There are no plants here, no trees or grass or any living thing that you can see, just bare stone under the red light. The terrain rises and falls in gentle slopes, creating low hills and shallow valleys that extend toward the horizon in every direction you look. Some of the rock surfaces appear smooth, possibly worn down by ancient processes, while others show sharp edges and rough textures, suggesting younger geological features. The sky color remains consistent as you look around, that peachy orange tone that comes from sunlight filtering through this planet's atmosphere, assuming it has one. Scientists on Earth remain uncertain whether TRAPPIST-1e has retained an atmosphere or lost it over billions of years to the star's radiation. If atmosphere exists here, it might be thin, perhaps similar to the air pressure on a high mountain on Earth. Enough to scatter light, but not thick enough to support life as we know it on the surface, without protection. The red sunlight changes how everything appears, shifting all colors toward the orange and red end of the spectrum, while muting blues and greens. Your gloved hand, held up before your face, looks rust-colored, rather than the white or grey the suit material actually is under normal light. The rocks at your feet show various shades of brown and rust and dark orange, though their true colors under white light might be quite different. Everything takes on this warm amber cast, and the effect creates a landscape that feels simultaneously familiar because the geology resembles deserts on Earth, and utterly alien because of the light that bathes it. Walking forward, you move across the rocky ground toward a slight rise perhaps 100 meters away, wanting to see the view from higher ground. Each step in the reduced gravity carries you a bit farther than the same effort would on Earth, giving your movements a slight bouncing quality. The ground beneath your boots feels solid and stable, ancient stone that has supported nothing but its own weight for billions of years. The silence around you is nearly complete, broken only by the sound of your own breathing and the faint hum of your suit systems. Reaching the top of the rise, you stop and look around at the expanded view, seeing farther now across the rust-colored landscape. The horizon appears closer than it would on Earth, because TRAPPIST-1e is slightly smaller, only about 92% of Earth's diameter. The curvature of this world is subtly more pronounced, creating a horizon that sits perhaps 4 kilometers away rather than the 5 kilometers you could see from the same elevation on Earth. The star remains in the same position in the sky that it held when you landed, unchanging, because this world is tidally locked to its star. Tidal locking means that TRAPPIST-1e always shows the same face to its star, just as the moon always shows the same face to Earth. One side of this planet remains in permanent day, bathed continuously in red sunlight, while the opposite side lies in permanent night, never seeing the star. The boundary between these regions, called the terminator, experiences perpetual twilight, with the star sitting forever on the horizon, neither rising nor setting. You have landed on the dayside, in the region of eternal afternoon, where the sun never moves and time is measured by instruments rather than by the passage of light across the sky. The subsolar point, the spot on the surface directly beneath the star where sunlight strikes most directly, lies somewhere to your east based on your current position. That location would be the hottest place on the dayside, receiving the most concentrated sunlight, though even there the temperature remains moderate because the star itself is cool and dim. Where you stand now, the temperature feels comfortable, warm but not hot, like a place where water could remain liquid if it existed here. The possibility of water, of oceans or lakes, or even just underground ice, remains one of the great unknowns about this planet. Looking again at TRAPPIST-1F hanging in the sky, you notice that it has moved slightly since you first saw it after landing. Or rather, you have rotated beneath it as TRAPPIST-1E turns on its axis. Wait, no, that is not quite right, because tidally locked planets do not rotate relative to their star. They keep the same face pointed toward it, always. But they do rotate relative to the other planets in the system, completing one rotation for each orbit around the star. TRAPPIST-1E orbits its star once every 6.1 Earth days. So from here, TRAPPIST-1F would appear to move slowly across the sky, taking days to cross from one horizon to the other as the orbital positions of both planets shift relative to each other. The star itself, TRAPPIST-1, appears roughly the same size in the sky as our Sun appears from Earth. Perhaps slightly larger, despite being much smaller than our Sun in actual diameter. This happens because TRAPPIST-1E orbits much closer to its star than Earth orbits the Sun, only about 3% of Earth's orbital distance. The star is tiny, only about 12% the diameter of our Sun, roughly the size of Jupiter in our solar system. But seen from this close distance, its apparent size grows to match the familiar solar disk we know from home, creating an odd sense of familiarity in this alien place. The warmth you feel, even through the suit's insulation, comes from this small red sun pouring out steady energy, less than 0.5% of our Sun's total output. But concentrated on this tight family of planets orbiting so close that energy is enough to warm worlds, enough perhaps to sustain liquid water, maybe even enough to allow life to develop under the right conditions. Scientists chose to study this system intensely because 3 of its 7 planets, including the one you stand on now, orbit within the habitable zone. The discovery of 7 Earth-sized planets around one star, with 3 potentially habitable, changed how we think about the prevalence of life-friendly worlds in the galaxy. Standing here under the red sun, 6 other Earth-sized worlds visible in the sky above, you begin to understand what makes this system so special, and why traveling here, even in imagination, feels like visiting the future of planetary exploration and the search for life beyond Earth. The silence holds no answers yet, just the patient presence of stone and star and sibling worlds hanging in the peachy sky. The exploration of TRAPPIST-1E's dayside continues as you trek westward, away from the subsolar point, moving gradually toward cooler regions, where the sun's angle becomes less direct. The landscape varies little at first, remaining rocky and barren, but the temperature begins to drop subtly as you travel further from the warmest zone. The suit's environmental systems adjust automatically to maintain comfort, but the external temperature reading shows the decrease, dropping a few degrees with each kilometer traveled. You are walking toward the terminator, the boundary between eternal day and eternal night, though that boundary still lies hundreds of kilometers distant from your current position. The geology here shows signs of volcanic origin, basaltic rock similar to the lava plains found on Earth's moon, or in the vast flood basalt provinces on Earth. Much of TRAPPIST-1E's surface likely formed from volcanic eruptions early in its history, lava flows spreading across the landscape and cooling into the dark stone you walk across now. Whether this world remains geologically active today, with molten rock still moving beneath the surface, remains unknown from Earth's observations and unknowable from your current surface position. Future missions with seismic instruments could answer that question, detecting earthquakes if they occur, revealing whether this planet's interior remains hot and dynamic or has cooled to stillness. Craters mark the surface in places, circular depressions, where asteroids or comets struck this world sometime in the past billions of years since its formation. The craters vary in size from small bowl-shaped divots a few meters across to larger structures spanning hundreds of meters from rim to rim. None appear fresh, all show signs of age, their edges softened by whatever erosion processes operate here. Perhaps just the patient work of temperature changes, causing rock to crack and crumble over geological time. The absence of obvious recent craters might indicate that the TRAPPIST-1 system has cleared most of its debris over its billions of years of existence. Or perhaps just that impacts occur rarely enough that seeing evidence of recent strikes requires more extensive exploration than this brief visit allows. Stopping to examine one crater more closely, you walk to its rim and look down into the depression, seeing darker rock exposed in the interior walls. The crater measures perhaps 50 meters across and 10 meters deep, a modest impact feature by planetary standards, but impressive standing on the edge. The floor shows a scattering of small rocks, fragments that might have broken from the walls over time, or might be pieces of the impactor that created this crater. The shadows inside stretch long under the low-angle red sunlight, creating areas of deeper darkness that contrast with the illuminated surfaces. Turning away from the crater, you look up again at the sky, where TRAPPIST-1 still hangs, now showing slightly more of its illuminated face than before as the orbital angles shift. The planet appears as a thick crescent, perhaps 1/3 illuminated, the rest dark but still faintly visible against the background sky. If TRAPPIST-1F has an atmosphere, sunlight reflecting off it might make the dark portion visible from here, a phenomenon called Earthshine when seen from the moon looking at Earth. From your position on TRAPPIST-1E, you are seeing TRAPPIST-1F in a phase that Earth never shows to moon observers, because Earth's relationship with its moon differs from the complex orbital dance of these 7 worlds. Other planets remain visible too, and checking the mission briefing data on your suit's display, you identify which disk is which, based on brightness and position. TRAPPIST-1D appears as a smaller disk near the star, perhaps 15% illuminated, showing a thin crescent that would be invisible from Earth, but stands out clearly here. TRAPPIST-1G, farther from the star than TRAPPIST-1F, shows as a smaller disk at a different position in the sky, maybe half illuminated from this vantage point. The geometry of 7 planets in tight orbits creates an ever-changing display of phases and positions, a sky that would never look the same way twice if observed over enough time. The question of life on these worlds remains entirely open, unanswered by any evidence available to human science, as of now, decades after the system's discovery. TRAPPIST-1e, where you stand, represents perhaps the best candidate among the 7 planets for hosting life, due to its position in the middle of the habitable zone. But position alone guarantees nothing, as Venus in our solar system demonstrates, sitting in the Sun's habitable zone, yet remaining hellishly hot and utterly lifeless. TRAPPIST-1e would need to have retained an atmosphere of the right composition, would need to have water, would need to have the countless other factors that allowed life to develop on Earth. And even then, life's emergence remains a mystery, not fully understood by science. Looking around at the barren landscape, you see no obvious signs of biology, no green plants or movement or anything suggesting living processes. But life on Earth exists in places that look barren at first glance. Microbes living in rock or underground, or in conditions that seem impossible. If life exists on TRAPPIST-1e, it might be microbial, might be deep underground, might be in places this brief surface exploration would never encounter. The absence of visible life in this location means very little in the larger question of this world's habitability, and the vast majority of Earth's surface, throughout most of its history, would have looked equally lifeless to a visitor examining only bare rock, far from any ocean or hydrothermal vent. Continuing westward, the Sun's position in the sky appears to lower slightly as you move toward the terminator, though the star does not actually move. Only your position on the surface changes relative to the subsolar point. The light takes on an even deeper red quality as the angle becomes more oblique and shadows lengthen across the rocky ground. Temperature continues to drop gradually, still comfortable but noticeably cooler than near the landing site, closer to the subsolar region. This temperature gradient drives atmospheric circulation, if atmosphere exists, warm air rising in the dayside regions and flowing toward the night side where it would cool and descend, creating winds that redistribute heat around the planet. The terrain begins to show subtle changes as you travel farther, the rock taking on slightly different colors, perhaps indicating different mineral compositions or different ages of lava flows. One area shows stone that appears almost black in the red light, while nearby regions remain the rusty brown color that dominates most of what you have seen. The black stone might be younger, more recent lava that has not yet weathered to the brown tones of older flows, or it might be compositionally different, rich in different minerals that create the darker appearance. Without laboratory analysis, the differences remain visible but unexplained, geological questions that would require dedicated study to answer. A vast plain stretches ahead, flatter than the terrain behind, extending for kilometers without significant elevation changes visible to the horizon. Walking out onto this plain feels like crossing a frozen ocean, the surface smooth and nearly level, perhaps an ancient lava lake that filled a low area and cooled into this flat expanse. Your boots leave faint marks in the fine dust that covers the solid rock beneath, the first footprints ever made here if no other visitor has come before. The dust is not thick, just a light coating, and the rock below shows through in many places where wind or some other process has cleared the surface clean. The terminator still lies far ahead, beyond the range of this day's exploration, but you can sense moving toward it in the changing light and cooling temperature. The boundary between day and night on a tidally locked world creates a unique environment found nowhere in our solar system except on our moon's poles, where some deep craters never see sunlight. At TRAPPIST-1E's terminator, the sun would sit perpetually on the horizon, neither rising nor setting, creating a band of eternal twilight, circling the planet between the bright dayside and the dark night side. That twilight zone might represent the most habitable region if extreme temperatures on the permanent day and night sides make those regions too harsh for life. Checking the mission timeline, you note that the exploration of the dayside must soon conclude to allow time for visiting the terminator region and the night side, completing the full picture of TRAPPIST-1E before moving on to other worlds. The dayside has revealed a rocky, geologically interesting world, bathed in red light, with comfortable temperatures and the constant presence of sibling planets in the sky above. No obvious signs of life have appeared, but nothing seen here rules out the possibility of biology somewhere on this world, perhaps in locations not yet visited, or perhaps hidden from surface observation entirely. The red sun hangs unchanging in its position as you turn to begin the journey toward the terminator zone, the boundary calling with its promise of eternal twilight. The dayside of TRAPPIST-1E has shown its character: rust-colored stone under peachy skies, warm and still and patient. Now the transition zone awaits, where light and dark meet and hold their endless border, where temperatures might be neither too hot nor too cold, but somewhere in between. The trek begins, carrying you away from the bright regions into the dimming light ahead. The landscape continues to unfold with each step, revealing more of this world's surface, more stone and dust, and the patient accumulation of geological time. Other planets wheel slowly overhead in their complex orbital dance. TRAPPIST-1 fell, growing slightly fuller as the hours pass and orbital positions shift. The star remains steady, its light reliable and constant, pouring energy onto this world as it has for billions of years and will for billions more. You walk through the alien afternoon that never ends, moving toward the edge of day, where another kind of permanent light holds sway. The journey from TRAPPIST-1E to its sibling world TRAPPIST-1F takes only hours in the spacecraft. The short distance between their orbits, allowing quick transfers in this compact system. You watch through the viewport as TRAPPIST-1E recedes behind, becoming a disk itself now, showing phases as the orbital angle changes your perspective. The star grows fractionally smaller as you move outward, the spacecraft traveling against the tiny gravitational pull toward an orbit further from the red dwarf. TRAPPIST-1F grows larger ahead, resolving from a point to a disk to a world, details of its surface beginning to show as the distance closes. Landing on TRAPPIST-1's dayside, you immediately notice the difference in light quality from TRAPPIST-1E. The illumination dimmer and redder here, because this world orbits farther from the star. The star appears smaller in the sky, noticeably less prominent than from the inner planet, though still bright enough to clearly illuminate the landscape around you. The temperature reads cooler on the external sensors, like autumn on Earth, rather than the spring-like warmth of TRAPPIST-1E. Comfortable, but with a definite chill. This world sits near the outer edge of the habitable zone, the region where temperatures begin to drop low enough that maintaining liquid water becomes challenging. Stepping out onto the surface, you find a landscape transformed, by cold, frost, coating many of the rocks you can see from the landing site. The terrain resembles TRAPPIST-1e in its rocky volcanic character. But here, ice has claimed the surface in many areas, white and crystalline, under the dim red light. The frost appears thickest in shadowed regions and thinner on surfaces directly facing the star, suggesting that even this far out, the red sun provides enough energy to keep some areas above freezing. Walking forward, your boots crunch slightly on the frost-covered ground, the ice perhaps a few millimeters thick in most places, coating but not burying the stone beneath. Looking up, you see TRAPPIST-1e hanging in the sky, now appearing from the outside as you appeared to them when viewing TRAPPIST-1f from that inner world. The planet shows as a crescent from this vantage point, perhaps 1/4 illuminated, smaller than TRAPPIST-1f, appeared from there because you have moved farther apart, increasing the distance. But TRAPPIST-1e remains clearly visible, a sibling world close enough that its features might be resolvable with a good telescope, or with enhanced vision from your suit's display. Other planets scatter across the sky too. The inner worlds, TRAPPIST-1b, C and D, clustered near the star, while TRAPPIST-1g lies farther out in the distance from your current position. The sky color here appears deeper and more saturated than on TRAPPIST-1e, less peachy and more purely red-orange, darker toward the zenith. Whether TRAPPIST-1 has an atmosphere remains uncertain. Observations from Earth unable to conclusively determine atmospheric retention for any of these worlds yet. If atmosphere exists, it might be thin enough that the sky looks darker than on Earth even during daytime, approaching the black of space that astronauts see from the moon. The dimmer light from the smaller appearing star contributes to the darker quality, less illumination scattered by whatever gases might surround this world. The frost covering much of the visible terrain suggests that water exists here, at least in frozen form, sublimating from ice to vapor, and perhaps condensing back to ice in endless cycles. Where this water came from originally remains a question common to all potentially habitable planets. Water delivered by comets during the system's early history or outgassed from the planet's interior during volcanic eruptions billions of years ago. The presence of surface ice on the dayside indicates that temperatures hover near the freezing point of water, warm enough in the sunniest spots to melt frost, cold enough in most areas to maintain ice. This narrow temperature range puts TRAPPIST-1f right at the boundary of conditions where liquid water could exist on the surface under the right circumstances. Walking toward a nearby ridge to gain a better vantage point, you notice how the reduced light makes the landscape feel quieter, more subdued than the brighter dayside of TRAPPIST-1e felt. The frost gives the terrain a softer appearance, smoothing the rough edges of rocks and filling small cracks and depressions with white ice. The ridge itself stands perhaps 20 meters high, a modest elevation change by mountain standards, but significant in this generally flat volcanic plain. Climbing it requires care in the ice-covered areas, your boots seeking purchase on bare rock where frost has sublimated or blown away, avoiding the slippery ice-coated surfaces where possible. From the top of the ridge, the expanded view reveals more frost-covered terrain, extending toward the horizon, with darker patches marking areas where bare rock shows through, or where the angle of sunlight has warmed surfaces above freezing. The subsolar point, the warmest location on the dayside, lies somewhere to the east from your current position, and you wonder if that region shows less frost. If the temperature there rises high enough for liquid water to persist in sheltered areas. the possibility remains speculative without direct observation. But the thought of liquid water somewhere on this world makes TRAPPIST-1 scientifically fascinating, despite its colder conditions compared to the more temperate inner neighbor. The geology, visible from this elevated position, shows the same volcanic origins as TRAPPIST-1e, lava flows creating the base terrain, with impact craters dotting the surface in scattered locations. One large crater appears in the middle distance, perhaps a kilometer across based on the scale of your surroundings, its rim rising above the surrounding plain. Ice appears especially thick inside that crater, the depression perhaps acting as a cold trap where frost accumulates and remains protected from the weak sunlight. Walking to that crater would take a couple of hours, and the mission timeline allows for some exploration before moving on to the Terminator and nightside regions of this world. Descending from the ridge, you head toward the large crater, crossing the frost-covered plain as the small red star watches from its fixed position overhead. The gravity here feels almost identical to TRAPPIST-1e, this world being slightly larger at about 104% of Earth's radius, but similar enough that the difference is barely noticeable. The frost crunches under your boots with each step, the sound transmitted through the suit's contact with the ground, since sound cannot travel through the vacuum or extremely thin atmosphere if this world has lost its air to space. Each footprint you leave shows dark stone beneath where the frost has compressed or been pushed aside, marking your path across the white expanse. The crater looms larger as you approach, its rim rising above you, the interior hidden until you climb high enough to see over the edge. The walk takes longer than estimated. The distance is deceptive in the reduced light and unfamiliar landscape. But eventually, you reach the crater's outer slope and begin climbing toward the rim. The slope is gentle, much less steep than it appeared from a distance. Layered rock showing through the frost in bands and ledges. The rocks here are dark, possibly older basalt exposed by the impact that created this crater, material excavated from below the surface lava flows. Reaching the rim, you stop and look down into the crater's interior, seeing a floor covered in thick white ice that nearly fills the depression. The ice appears meters thick in places based on the smoothness of the surface and the way it has filled irregularities in the crater floor. This ice might have accumulated over millions or billions of years, frost condensing here and never melting, slowly building up layer by layer until creating this frozen lake. Whether liquid water lies beneath the surface ice remains impossible to determine without drilling or seismic investigation. But the possibility of a subsurface ocean, or even just a pocket of liquid water hidden under this frozen surface, cannot be ruled out. The view from the crater rim provides a panoramic look at the surrounding landscape, frost-covered plains extending to the horizon in most directions, with scattered ridges and smaller craters breaking the general flatness. The star hangs in its unchanging position, smaller than from TRAPPIST-1e, its dimmer light creating longer, darker shadows that stretch across the terrain. TRAPPIST-1e remains visible in the sky, now showing a slightly different phase than earlier, as both planets continue their orbital paths around the central star. The beauty of this ice-covered world under the dim red sun carries a peaceful, still quality, like winter twilight frozen in time. Looking at the other visible planets, you identify TRAPPIST-1d, showing as a small crescent near the star, and TRAPPIST-1g further out, showing more illumination, perhaps half-lit from this viewing angle. The inner planets, TRAPPIST-1b and c, are difficult to separate from the star's glare, even from this outer vantage point. Their orbits so tight that they appear almost merged with the stellar disk. 7 worlds in total circle this small red star, and from each world you can see most or all of the others depending on their current positions. A planetary system where every world has company in the sky, where no planet orbits in loneliness. The ice in the crater, the frost on the rocks, the comfortable if cool temperature all suggest that TRAPPIST-1 F sits right at the edge of habitability. Possibly too cold for surface life, but perhaps perfect for life beneath the ice if liquid water exists there. The same tidal forces that cause this planet to always show one face to its star also cause internal friction and heating through the flexing of rock and metal in the planet's interior, a process called tidal heating. This heating might be enough to maintain liquid water below the frozen surface, creating an environment similar to Jupiter's moon Europa or Saturn's moon Enceladus in our solar system. Icy worlds hiding liquid oceans beneath their frozen shells. Turning away from the crater, you head back toward the landing site, the exploration of TRAPPIST-1 F's dayside, showing a world in the grip of cold but not entirely frozen. Water existing here as ice on the surface and potentially as liquid below. The dimmer star, the lower temperatures, the frost-covered landscape all mark this as a different environment from TRAPPIST-1e, colder and perhaps more challenging for life, but not impossible. The journey continues as the Terminator awaits, where even colder conditions prevail. And beyond that, the night side holds its frozen darkness under stars never dimmed by sunlight. Traveling west across TRAPPIST-1F's surface, away from the regions of pale illumination and into the dimming light toward the Terminator, the temperature drops steadily with each kilometer covered. The frost that covered parts of the dayside becomes ubiquitous here, coating every surface, thick white ice smoothing the landscape into gentle contours. The star, already small and dim from this planet's orbital distance, appears to sink toward the horizon as you approach the boundary between day and night. The light takes on a deep crimson quality, almost the color of blood diluted in water, a red twilight that seems to stretch time itself into stillness. The Terminator zone on a tidally locked world creates a unique environment found nowhere else. A band circling the planet, where day and night meet and hold their border forever. The sun sits permanently on the horizon here, half visible above the edge of the world, half hidden below, never rising higher and never setting completely. The illumination comes at such a low angle that shadows stretch for kilometers, and much of the ground lies in permanent shade cast by even modest surface features. The temperature in these shadowed regions drops far below freezing, while areas directly illuminated by the weak sunlight remain merely very cold rather than frozen solid. Reaching a point where the star sits perhaps 10 degrees above the horizon, you stop to observe the environment of deep twilight. Ice covers everything visible. No bare rock shows through anywhere within sight. The entire landscape claimed by frozen water. The ice appears smooth in some areas and rough in others, possibly snow-like frost deposited from atmospheric water vapor, if this world has retained enough gas to create weather. The temperature reads -40 degrees Celsius on the suit's external sensors, cold enough that any exposed liquid water would freeze within seconds, cold enough that even carbon dioxide would begin to condense if it existed in the thin atmosphere. Looking at the star, you notice how its disk appears distorted and flattened by the extreme low angle of view. Atmospheric refraction, if an atmosphere exists here, bending the light and changing the sun's shape. The crimson light streaming across the frozen landscape creates an otherworldly scene, shadows and light mixing in gradients of red and darkness. Long streamers of light stretch between the prominences of rock and ice that block the direct solar illumination, creating patterns across the frozen ground, like the rays of a distant sunset that will never complete. The sky here shows stars, even though the sun remains above the horizon. The combination of the dim red star and the darker sky, allowing bright stars to become visible during the daytime twilight. Looking up, you see stars scattered across the dark red-purple sky, more of them visible toward the east, where night begins, fewer toward the west, where the dayside's slightly brighter illumination washes them out. Planets remain visible too. TRAPPIST-1e, showing as a bright crescent in a different part of the sky than earlier, its position shifted by the hours of travel to this location. TRAPPIST-1g appears larger now, easier to see from this angle, showing perhaps 3/4 illumination. Walking forward toward the terminator itself, where the sun would sit precisely on the horizon, the temperature continues to drop, reaching -50 degrees and still falling. Ice crystals glitter in the weak sunlight, the frost taking on a sparkling quality where the low-angle light strikes it directly. Your boots leave deep impressions in the frost-covered surface. The ice here thick enough that compressing it requires force, creating footprints that might remain unchanged for millions of years if nothing disturbs them. The thought of your passage, leaving a permanent mark on this world, carries a strange weight, evidence of your presence, outlasting civilizations. The boundary itself, the true terminator, appears ahead as the line where the sun's lower edge touches the horizon precisely. The landscape there disappears into a gradient of deep shadow, the sun providing just enough light to hint at terrain features, but not enough to reveal details clearly. Standing at this exact boundary, you would have 1 foot in the daylit hemisphere and 1 foot in the night side regions, straddling the line between two permanent states. But approaching too closely to the night side risks entering regions where the cold becomes truly extreme, where even the protective systems of the exploration suit might struggle to maintain safe internal temperatures. Instead, you turn and begin traveling south, following the terminator band, staying in the region where the sun hovers just above the horizon, but never quite sets. This twilight belt circles the entire planet, a ring of eternal sunset sunrise, where conditions remain constant but harsh, too cold for liquid water on the surface, but perhaps warmer than the night side's frozen depths. If TRAPPIST-1f has retained an atmosphere thick enough to transport heat around the planet, winds would blow constantly here, air moving from the warmer day side toward the colder night side, creating a circulation pattern driven by the temperature difference between the permanent hemispheres. Traveling along the terminator reveals how this zone is not a thin line, but rather a broad band, where twilight holds in gradients from dim light to near darkness. The width of this band depends on how much atmosphere exists to scatter and refract sunlight around the planet's curvature. thick air creating a broader twilight zone than thin air or vacuum would allow. If TRAPPIST-1F has lost its atmosphere to space over the billions of years since formation, the terminator might be quite narrow, perhaps only a few kilometers wide, a sharp transition from day to night. If atmosphere remains, the twilight band could extend hundreds of kilometers, creating a substantial region of intermediate conditions. The landscape in the terminator zone shows features shaped by the unique conditions of permanent twilight, though without more extensive exploration or better lighting, determining the exact nature of these features remains challenging. Some areas appear to show parallel ridges running roughly north-south, possibly wind-carved formations created by the persistent circulation from day to night side, though geological processes could create similar structures. Other regions show smoother terrain, the ice there perhaps deposited more recently or shaped by different processes than the rougher areas. Every feature remains under deep red twilight, shadows and light creating ambiguity that would resolve under brighter illumination, but here remains mysterious. Looking back toward the dayside, the terrain there appears fractionally brighter, the increased angle of sunlight making a visible difference even though the star remains low to the horizon in that direction too. Looking forward into the night side, darkness deepens until features disappear entirely into black. The absence of sunlight, creating conditions where only starlight and planet light from the other worlds in the system provide any illumination at all. The transition is gradual but inexorable. The mathematics of geometry and the physics of light, creating a boundary as definite as any political border, yet entirely natural and unchanging. Deciding to cross into the night side to complete the exploration of TRAPPIST-1F, you begin walking east, moving away from the dim red star and into the deepening darkness ahead. The temperature drops noticeably with each step. -60 degrees, -70, approaching -80 Celsius as you leave the last direct sunlight behind. The suit's environmental systems work harder to maintain internal warmth, and you monitor the power levels carefully, ensuring enough reserve remains for the return journey and the continued mission. The ice beneath your boots becomes harder, more solid, frost compressed by the extreme cold into something approaching glacial ice in density and structure. The transition into full night happens gradually over perhaps 15 minutes of walking. The sun's disk dropping below the horizon behind you, the crimson light fading to a deep red glow, and then to darkness. Stars blaze overhead suddenly, dramatically, thousands of them appearing as the last scattered sunlight disappears and your eyes begin adjusting to the darkness. The Milky Way arches across the black sky, brilliant and detailed. More stars visible here than from almost anywhere in our solar system, except perhaps from the most distant reaches beyond Pluto. The night side of TRAPPIST-1F holds you in its frozen embrace, and the stars watch in patient silence. Looking up, you identify the other planets by their brightness and positions. TRAPPIST-1e, shining brightly as a thick crescent, its dayside facing partially toward you and partially toward the star, creating a phase similar to Venus, showing its crescent face to Earth. TRAPPIST-1g appears almost full from this angle, its entire dayside visible from your position on TRAPPIST-1F's night hemisphere. The inner planets, TRAPPIST-1b, C, and D, cluster together near where the sun set, their light mingling with the faint glow still lingering at the western horizon. from the star just below the edge of the world. The temperature has stabilized at around -90 degrees Celsius, cold enough to freeze carbon dioxide into dry ice, if the atmosphere contains any. Cold enough that nitrogen would begin to liquefy under the right pressure conditions. This is the permanent state of TRAPPIST-1F's night side, a frozen wasteland under stars, receiving no warmth from the distant hidden sun. Whether the cold is uniform across the entire night hemisphere, or whether some regions are slightly warmer due to atmospheric heat transport from the dayside remains unknown without more extensive exploration. But here, at least, the cold reigns absolute, and nothing could survive on the surface without protection. The landscape is barely visible, your suit's lights illuminating a small area around you, showing ice and more ice, an endless frozen plain. Using the suit's infrared sensors, you scan the area and find no significant heat sources, no warm spots that might indicate volcanic activity or tidal heating reaching the surface. The planet seems geologically quiet, or at least this region shows no signs of internal heat escaping to warm the frozen ground. The ice layer might be kilometers thick here, accumulated over billions of years. All the water that once existed on the night side condensed and frozen into these permanent deposits. Turning back toward the west, you begin the return journey toward the Terminator, and eventually the dayside, the exploration of TRAPPIST-1's night hemisphere, complete. This world has shown itself to be a planet of ice, cold even on its dayside, frozen solid on the night hemisphere, living at the edge of conditions where life might barely persist. Subsurface oceans remain possible. Tidal heating might maintain liquid water deep below the ice. But the surface offers no hospitality to biology as we understand it. The journey continues as other worlds await, warmer planets and colder ones. A system of 7 Earths showing every variation of habitability from scorched to frozen. The spacecraft lifts away from TRAPPIST-1F, leaving the ice-covered world behind, and turns inward toward a planet closer to the red dwarf star, toward TRAPPIST-1d, which orbits at the inner edge of the habitable zone. The journey takes only a brief time, the compact arrangement of planets making travel between them almost routine, compared to the vast distances separating worlds in our solar system. Through the viewport, TRAPPIST-1d grows larger, a world roughly 3/4 Earth's size, smaller than the previous 2 planets you have visited, but no less interesting for being more compact. The star grows larger too, in the viewing angle, appearing brighter and more prominent as the spacecraft falls inward toward the tighter orbit. Landing on TRAPPIST-1d's dayside, you step out into light that feels noticeably brighter and warmer than on TRAPPIST-1F, closer to the quality of illumination on TRAPPIST-1e, but with a subtle difference in intensity. The temperature reads warm, perhaps too warm for comfort during extended surface time, approaching 40 degrees Celsius in the direct sunlight here on this closer orbit. The landscape shows bare rock, reddish-brown stone baked by the star's radiation, with no sign of the frost and ice that dominated TRAPPIST-1F's terrain. This world sits right at the boundary of habitable and too hot, a threshold planet where small differences in atmospheric composition or surface properties might determine whether liquid water can exist or whether this world is too scorched for biology. The smaller size of TRAPPIST-1d is immediately noticeable in the horizon's curvature, the visible edge of the world, closer than on the larger planets you have explored so far. Standing on the surface, You can see perhaps only 3.5 kilometers to the horizon, the small world revealing its curvature more obviously than Earth-sized planets would. The reduced gravity feels lighter, perhaps only about 60% of Earth's pull, making movements easier and giving each step a slight bouncing quality, more pronounced than on the larger worlds. The star hangs in the sky larger than from TRAPPIST-1e, its disk taking up more of the view, the red dwarf's heat more intense here at this reduced distance. Looking up at the sky, you see the now familiar sight of other planets scattered across the salmon-orange expanse. TRAPPIST-1e appearing as a half-lit disk, showing its partial face. TRAPPIST-1f visible farther from the star, showing a thinner crescent. The innermost planets, TRAPPIST-1b and c, orbit closer to the star than this world, and from here they should be visible, but locating them against the solar glare proves difficult. The outer planets, TRAPPIST-1, G and H, appear small and distant, their farther orbits making them less prominent in the sky from this inner vantage point. The view confirms your position in the middle of the system, inner worlds sunward and outer worlds farther out, a sense of being neither at the extreme heat nor the extreme cold, but at a boundary between. The geology visible around the landing site shows volcanic origins like the other planets. Basaltic lava flows, creating the base terrain with scattered impact features, and what might be ancient volcanic vents or cinder cones rising from the plains. One feature catches your attention, a long winding channel cutting through the landscape, perhaps a kilometer away, possibly an ancient lava channel, or potentially a dry riverbed carved by flowing water billions of years ago. The possibility of liquid water in TRAPPIST-1d's past makes this channel worth investigating, and you set off across the rocky ground toward the feature. Boots crunching on the sun-baked stone, the heat becomes more noticeable as you walk. The suit's cooling systems working to maintain comfortable internal conditions, while the external temperature hovers around 40 Celsius in the direct sun. Shadowed areas behind rocks show slightly lower temperatures, but the relief is modest. The ambient heat from the warm ground and the thin atmosphere, if it exists, keeping everything well above comfortable levels. This temperature puts TRAPPIST-1d right at the edge of where liquid water could theoretically exist, too hot in direct sunlight, but possibly cool enough in shaded areas or in subsurface caves to maintain liquid state. Reaching the channel, you find yourself standing on the rim of a feature that cuts several meters deep into the surrounding terrain, running roughly east-west across the landscape. The channel bottom shows smooth surfaces in some areas and rougher textures in others, exactly what you might expect from either a lava channel or a water-carved riverbed, depending on interpretation. Without detailed analysis, determining which process created this feature remains impossible, but the morphology could fit either explanation. If water once flowed here, it would have been early in TRAPPIST-1d's history, when the planet might have had a thicker atmosphere and cooler surface temperatures, before stellar radiation stripped away the protective air and left the surface exposed to harsh conditions. Descending into the channel, you walk along its bottom for several hundred meters, examining the walls and floor for any additional clues about its origin. The walls show layering in some areas, bands of different colored rock stacked horizontally, suggesting multiple episodes of deposition, whether from lava flows or sedimentary processes. The floor remains relatively smooth, Any small irregularities worn down by some process, or perhaps never forming if the channel was created by flowing lava that cooled smoothly. Looking ahead, the channel extends toward the horizon, possibly continuing for many kilometers beyond your current position, a major feature on this small world's surface. Climbing out of the channel, you continue exploring the dayside terrain, moving toward the subsolar point region where the star would shine most directly overhead, and temperatures would reach their maximum values for this hemisphere. The landscape varies little from what you have seen so far. Rocky plains with scattered features, breaking the general monotony. No dramatic mountains or deep valleys visible from your surface-level perspective. The small size of TRAPPIST-1d might limit the geological processes that create major topographic features on larger worlds, less internal heat available to drive plate tectonics or massive volcanism, the planet possibly cooling more quickly than its larger siblings did. Approaching an area where the star sits nearly overhead, the temperature climbs above 45 Celsius, approaching 50 degrees in the most directly illuminated spots. This heat would be dangerous to exposed skin, hot enough to cause burns with prolonged contact, and you understand why this planet sits at the inner edge of habitability rather than comfortably within it. If TRAPPIST-1d has lost its atmosphere to stellar wind and radiation over billions of years, surface temperatures would vary wildly between day and night sides, too hot on one side and too cold on the other. If some atmosphere remains to redistribute heat, conditions might be less extreme, but still challenging for liquid water and life. The question of atmosphere for these planets remains one of the most important unknowns in understanding TRAPPIST-1 system's habitability. Red dwarf stars like TRAPPIST-1 produce powerful flares and intense ultraviolet radiation, especially during their youth, and this radiation can strip away planetary atmospheres over geological time. Rocky planets, this close to their star, face constant assault from stellar wind and radiation. And whether they retain protective envelopes of air depends on many factors, including the planet's magnetic field strength, its gravity, and the exact history of stellar activity. Observations from Earth using telescopes like James Webb Space Telescope can detect atmospheric signatures, if they exist. But as of the time these explorations are imagined, definitive answers remain uncertain for most of the TRAPPIST-1 worlds. Looking at the sky again, you notice TRAPPIST-1e showing a different phase than earlier, the changing orbital positions causing the illumination angle to shift, now showing perhaps 60% of its disk lit from this viewing angle. The continuous orbital motion of 7 planets around the small red star creates an ever-changing sky, planets moving through their phases as seen from each other, alignments and configurations that never repeat exactly the same way. Watching the sky from TRAPPIST-1d over days or weeks would reveal this complex dance, planets passing each other in their orbits, some moving faster in their inner tracks and others slower in the outer lanes, all bound together by the central star's gravity. Deciding to move toward the terminator to see how conditions change at the boundary between day and night, you begin walking westward, away from the subsolar point and its intense heat. The temperature drops gratefully as you leave the hottest region behind, the star's angle becoming less direct, the heat less oppressive. The rock beneath your boots remains warm, radiating stored energy absorbed during the endless day under the red sun. But the air temperature, if atmosphere exists, drops noticeably, The landscape continues its rocky monotony, ancient lava plains extending kilometer after kilometer with minimal variation. As the Terminator zone approaches, marked by the lowering star approaching the horizon ahead, the temperature becomes more comfortable, dropping below 30 degrees Celsius and continuing to fall. The light takes on the familiar deep red quality of twilight, though here that twilight is permanent rather than a brief transition between day and night. Shadows lengthen across the ground, cast by even small rocks and surface irregularities, the low-angle sunlight creating exaggerated relief that makes the terrain appear more dramatic than under direct overhead illumination. Stopping at a point where the sun sits perhaps 15 degrees above the horizon, you observe the Terminator environment on this inner habitable zone world. The temperature here reads comfortable, around 20 degrees Celsius, warm enough for liquid water, if any existed, and if atmospheric pressure allowed it. This twilight band might represent the most habitable region on TRAPPIST-1d, neither too hot like the subsolar point, nor too cold like the night side, a compromise zone where conditions could theoretically support life. If this planet has retained its atmosphere, winds would blow constantly through this region, air circulating from day to night, side and back again, driven by temperature differences and the rotation-less state of this tidally locked world. Standing here in the eternal red twilight, you sense that this boundary region holds the key to TRAPPIST-1d's habitability prospects. The narrow band where extremes meet and cancel to create moderation. The night side beckons, and crossing into it reveals the expected pattern. Temperature dropping rapidly as darkness deepens. The stars' light fading below the horizon. Stars appearing overhead in increasing numbers. The night hemisphere of TRAPPIST-1d mirrors the night sides of the other planets explored, cold and dark and dominated by starlight and the presence of sibling worlds in the sky. TRAPPIST-1e shines brightly from this darkened vantage point, appearing larger than before, showing significant phases that change its appearance from how it looked from the dayside. TRAPPIST-1f appears smaller and farther away, a companion world hanging in the darkness alongside the brilliant stars of the Milky Way. The temperature stabilizes around -40 Celsius. On the night side, cold but not as extreme as TRAPPIST-1's frozen night hemisphere, this inner world remaining warmer overall due to its closer proximity to the star, and possibly due to better atmospheric heat redistribution if air exists here. Ice might accumulate in the coldest regions, frost deposited where temperature drops below water's freezing point, but the night side of TRAPPIST-1d likely remains less thoroughly frozen than the outer habitable zone planets experience. Walking carefully in the darkness, illuminated only by suit lights and the faint glow of planets overhead, you complete the circuit of this threshold world, experiencing its full range from too hot to too cold, with a narrow, comfortable zone between. TRAPPIST-1d has revealed itself as a world balanced on the knife edge of habitability, its smaller size and inner position creating conditions that might be too extreme for life, or might, in the right configuration, support biology in the twilight zones. The channel carved into its surface hints at a possible wetter past, water flowing here before changes in atmosphere or solar radiation made liquid water impossible. As you return to the spacecraft for the journey to the next world, TRAPPIST-1d remains behind, its eternal day slowly baking under the red sun, its eternal night cooling in darkness, the boundary between holding whatever chances this world has for harboring life. The spacecraft climbs outward from TRAPPIST-1D's orbit, moving against gravity's pull toward the outer reaches of the habitable zone where TRAPPIST-1G circles the red dwarf star. This journey takes longer than the short hops between inner planets, the increased distance requiring more time even in this compact system where all 7 worlds orbit closer to their star than Mercury orbits our Sun. Through the viewport, the star slowly diminishes in apparent size as the spacecraft gains altitude in the gravitational well. TRAPPIST-1G growing from a point to a disk ahead. This outer habitable zone world represents the last of the potentially life-friendly planets before the frozen frontier of TRAPPIST-1H begins, a boundary between possible and impossible for biology as Earth understands it. Landing on TRAPPIST-1G's dayside, the immediate impression is one of cold, the temperature reading far below freezing, even in the direct sunlight of the distant star. The star itself appears small in the sky, noticeably dimmer than from any previous landing, its dull red disk providing weak illumination that barely warms the surface below. Ice covers everything visible, thick white frost coating every rock, filling every depression, smoothing the landscape into gentle curves and mounds. This world sits at, or just beyond the outer edge of the habitable zone, the region where stellar energy becomes too weak to maintain liquid surface water even under ideal atmospheric conditions. The temperature hovers around -20 Celsius at the subsolar point, the warmest location on the entire dayside, and drops from there into deeper cold. Stepping onto the frozen surface, your boots sink slightly into the thick frost, creating footprints that compress the ice crystals without melting them. The gravity here feels similar to Earth's, this planet being larger than Earth at about 113% of Earth's radius, making it the largest of the TRAPPIST-1 planets visited so far. The increased size might help this world retain atmosphere, if it ever had. One, the stronger gravity, making it harder for stellar wind to strip away protective gases. Whether that advantage has proved sufficient to maintain air over billions of years remains unknown, but the thick ice covering the surface suggests that water at least exists here in abundance. Frozen now, but potentially liquid beneath the surface, if tidal heating warms the interior. Looking up, the sky appears very dark, even though the sun shines. The combination of weak illumination and possibly thin atmosphere, creating a deep reddish-purple color that fades towards black at the zenith. Stars are visible even in this daytime sky, bright points scattered across the darkness. The familiar pattern of the Milky Way, faintly visible as a lighter band arching overhead. The inner planets cluster together near the small red star, TRAPPIST-1, B, C, D, E, and F, all visible as a group, their relative brightness and positions creating a mini constellation unique to this outer vantage point. TRAPPIST-1H should be visible too, further out from your current position, but locating it among the stars requires careful observation or reference to the mission data. The landscape around the landing site shows ice-covered plains extending to the horizon, with occasional low ridges and scattered rocks breaking the general flatness. The ice appears old, undisturbed, surface features suggesting accumulation over immense periods of time, without any melting or liquid flow to reshape the deposits. Some areas show what might be sastrugi, wind-carved features in the ice similar to those found in Antarctic snowfields on Earth, parallel ridges, and grooves aligned with prevailing wind direction. If these are indeed wind features, they suggest that TRAPPIST-1G has retained at least some atmosphere, enough to create surface winds that shape the ice over time. Walking toward one of the larger ridges visible from the landing site, you notice how the low angle of sunlight creates dramatic shadows, the weak red light barely penetrating the shadowed areas where darkness deepens to near total black. The temperature difference between sun and shade reads significant on the sensors. Sunlit areas perhaps -20 Celsius, while shadowed regions drop to -40 or colder. These temperature gradients might drive atmospheric circulation. If air exists, warm air rising in the lit areas and cold air sinking in the shadows, creating winds that blow constantly across the frozen landscape, following the patterns of light and dark. The ridge itself rises perhaps 30 meters above the surrounding plain, a modest elevation gain that nevertheless provides a significantly expanded view of the surrounding territory. Climbing it proves easier in the reduced effective weight, despite your mass being the same. The strong gravity of this large planet pulling firmly, but the climbing effort reduced by the suit's assistance, and the good traction provided by the ice. Reaching the top, you stop and scan the horizon, seeing ice and more ice in every direction. The frozen dayside of TRAPPIST-1G, extending hundreds of kilometers toward the terminator somewhere beyond the visible horizon. The star hangs small and dull in the sky, providing light but little warmth, its energy insufficient at this distance to reverse the deep cold of this outer world. From this elevated position, you notice what might be cracks or fissures in the ice in several areas visible across the landscape, dark lines cutting through the white surface. These could be cracks from thermal expansion and contraction as areas warm slightly under the weak sun and cool again in shadow. Or they could be more geologically interesting features, fissures where tidal heating from the planet's interior has caused the ice to fracture and perhaps allow subsurface liquid to reach the surface before freezing. The possibility of cryovolcanism, ice volcanoes erupting liquid water, or slushy ice from below, makes TRAPPIST-1G scientifically fascinating, despite its surface appearing completely frozen and dead. Tidal heating might be the key to TRAPPIST-1G's potential habitability, despite the surface cold. The gravitational interactions between this planet and its 6 siblings, along with the star itself, cause the planet's shape to flex slightly as it orbits, the rock and metal interior deforming and relaxing in rhythm with the orbital period. This flexing generates heat through friction, warming the deep interior and possibly maintaining liquid water oceans beneath the frozen shell kilometers below your feet. The same process operates on Jupiter's moon Europa and Saturn's moon Enceladus in our solar system, creating subsurface oceans beneath ice shells on worlds far from the sun's warmth. If TRAPPIST-1G harbors such an ocean, it could potentially support life in the dark water below, organisms living on chemical energy rather than sunlight. Biology hidden from surface observation. Descending from the ridge, you decide to investigate one of the visible fissures, walking carefully across the ice toward a crack that appears to cut at least a meter deep into the frozen surface. The approach requires care, uncertain whether the ice around the fissure remains stable or might collapse under weight, but the thick frost seems solid and well frozen. Reaching the edge, You look down into the crack and see darker ice in the depths, possibly older material exposed by the fracture, or possibly contamination from below. Minerals or organic compounds coloring the pure water ice. The fissure extends in a relatively straight line across the landscape, cutting through surface features without deviation, suggesting a deep origin rather than a shallow surface crack. Kneeling beside the fissure, you examine the ice more closely, seeing crystalline structure in the frost. Individual ice crystals visible where the low-angle sunlight catches their facets. The ice appears pure white near the surface, suggesting it formed from water vapor condensing directly from atmosphere to solid, without liquid phase, a process called deposition. Deeper in the fissure, the ice shows the darker color, possibly compressed by the weight of overlying layers or altered by time and pressure into different crystalline forms. Taking a sample would require drilling equipment not available on this exploratory mission, but the observation and documentation provide data for future study. Standing and continuing the exploration, you walk along the fissure's length, following it toward the terminator region where the star approaches the horizon and light fades into deeper twilight. The fissure continues for kilometers, never closing, a persistent feature cutting across the frozen plains. Other similar features become visible as your eyes adjust to the pattern. This landscape crisscrossed with fractures and cracks, creating a web of lines across the ice. The pattern suggests active geology below, movement and stress in the ice shell as tidal forces work on the planet's interior. Evidence supporting the possibility of subsurface liquid and ongoing geological processes, despite the frozen surface appearance. The terminator zone on TRAPPIST-1G appears ahead as the star drops toward the horizon, its small disk touching the edge of the world and casting the already weak light at an even more oblique angle. The temperature drops noticeably as you approach, -30, -40, continuing to fall as direct sunlight becomes more grazing and finally disappears entirely. The twilight here glows very faint and deep red, the star providing almost no illumination once it drops below the horizon. Just a faint reddening of the sky in the direction of the hidden sun. The transition to night happens more abruptly than on the inner planets, the weak star unable to create a broad twilight zone through atmospheric scattering. Crossing into the night side, darkness envelops the landscape quickly, stars appearing brilliant and sharp in the black sky overhead. The temperature plummets to -70 Celsius and continues dropping, the night side of this outer world experiencing cold second only to TRAPPIST-1H in the system. Ice here is rock hard, compressed, and frozen solid. The surface probably unchanged for billions of years, except where internal processes cause fissures and cracks. Walking in the darkness requires careful navigation. The suit's lights providing local illumination, but the vast frozen expanse remaining hidden beyond the limited range of artificial light. The planets shine brightly in the night sky, especially the inner worlds which appear from here as bright crescents or half-lit disks, depending on their current orbital positions. TRAPPIST-1e, the most Earth-like world, shines prominently, appearing larger than Venus looks from Earth, and showing significant phases that reveal its spherical shape clearly. TRAPPIST-1f appears nearby in the sky, slightly smaller and showing different illumination. The innermost planets, TRAPPIST-1b and c, appear close to the star's position below the horizon, their light mingling with the faint glow of the hidden sun. TRAPPIST-1h should be visible somewhere in the darkness, farther out and fainter, completing the family of 7 worlds. Standing in the frozen darkness, you consider the possibility of life beneath your feet, organisms living in liquid water kilometers below the ice, sustained by tidal heating and chemical energy from the planet's interior. Such life would never see the stars that shine so brilliantly overhead, would never know the red sun that provides this system's energy, would exist in permanent darkness, warmed by the planet's own heat. But if life can exist in such conditions, the number of potentially habitable worlds in the galaxy increases dramatically. Every ice-covered planet, with tidal heating, becoming a possibility regardless of surface temperature. TRAPPIST-1G might be dead on its frozen surface, but alive in its hidden ocean, biology persisting in one of the galaxy's countless dark seas. The exploration of TRAPPIST-1G concludes as you return to the spacecraft, leaving the frozen outer habitable zone, world to its ice and darkness and potential hidden life. This planet has shown that habitability extends beyond simple surface temperature calculations, that liquid water can exist far from a star's warming light if other energy sources maintain it. The journey continues outward to even colder worlds, but first, a turn inward toward the scorching planets that orbit closest to the red dwarf, where heat replaces cold as the dominant challenge to existence. The spacecraft turns inward from the outer system, diving deep into the gravity well toward the innermost planet, TRAPPIST-1b, which orbits so close to the red dwarf star that its year lasts only 1.5 Earth days. The journey inward feels like falling, the star growing rapidly in the viewport, its light intensifying, the heat increasing as instruments register the rising temperature of nearby space. TRAPPIST-1b emerges ahead, a world tidally locked, like all its siblings, but subjected to far more intense radiation and heat than any of the potentially habitable planets you have explored. This is a scorched world, the closest to the star, the first planet in the system, and possibly the most extreme in its conditions. Landing on TRAPPIST-1b's dayside requires special thermal shielding, the surface temperature reading above 400 degrees Celsius, hot enough to melt lead, hot enough that rock might soften or even begin to melt in the most directly heated areas. The star dominates the sky, appearing enormous from this close vantage point. Its disk perhaps 20% larger in apparent size than the Sun appears from Earth, despite being much smaller in actual diameter. The proximity makes up for the small size, the red dwarf filling a huge section of the sky overhead, its heat palpable through every sensor. The light blazes red-orange, intense despite the star's cool temperature. The sheer closeness overwhelming the coolness with raw radiant energy. Stepping out onto the surface requires the spacecraft's protection, remaining nearby as a heat shield. The direct exposure to this environment limited by the suit's capabilities. The ground beneath your boots radiates heat upward, the rock temperature even higher than the ambient air or vacuum temperature, the stone baked by billions of years of continuous irradiation. The surface appears dark and glassy in places, rock that has melted and refrozen repeatedly, volcanic glass created not by volcanism, but by the star's heat melting the very crust of the planet. Other areas show rougher texture, stone that remains solid but stressed by thermal expansion, cracking and breaking under the constant heating and the temperature variations between areas in direct sunlight and rare shadowed spots. The landscape extends in shades of dark grey and black. The rock composition, likely similar to the volcanic basalt found throughout the system, but modified by the extreme conditions here. No ice exists on TRAPPIST-1b. No atmosphere persists if one ever existed. The stellar wind and intense heat, having stripped away any gases and any volatile materials billions of years ago. What remains is a core of rock and metal, tidally locked, one side forever burning under the close red sun, and the other side cooling in darkness, but still hot from the heat conducted through the planet's interior and radiated from the deep rock. Looking up at the star, you notice details invisible from farther out. Darker patches on the photosphere, where convection creates cooler regions, brighter areas where heat wells up from the star's interior. The star's surface appears mottled, not uniform. The natural variation in stellar atmospheres, visible from this proximity. Flares occasionally erupt from red dwarf stars, sudden brightenings that can increase the star's output substantially for minutes or hours, and TRAPPIST-1 has shown this behavior, though whether a flare occurs during your brief visit remains a matter of chance. The star churns and boils in slow motion, convection moving energy from the fusion-burning core to the radiating surface. The mechanics of stellar physics visible in the structure of light and shadow on the red disk. Other planets should be visible even from here, though finding them against the overwhelming glare of the nearby star challenges the eyes and instruments. TRAPPIST-1c orbits just beyond this innermost world, and it might appear as a disk somewhere in the sky away from the star's position, showing phases as viewed from this inner vantage point. The outer planets would appear even smaller and harder to see, their distance and the light scattering effects of being so close to the star making observation difficult. The sky itself appears darker here than on outer planets. Less atmosphere or dust to scatter light. The darkness of space, pressing close despite the blazing star filling part of the view. The temperature readings climb as you move away from the spacecraft's shadow, approaching 450 Celsius in areas of direct exposure to the star's face. This heat exceeds the operating limits of many materials, requires special thermal protection, limits exploration to brief excursions rather than extended surface time. The rock underfoot might be molten just below the surface, a crust of cooled stone over partially liquefied deeper layers. The geology of this world more akin to volcanic hot zones on Earth than to normal planetary surfaces. Walking carefully, you test each step, ensuring the ground remains solid, aware that this surface might hide pockets of molten rock just beneath the crust. Craters dot the landscape where visible, impact features created when asteroids struck this world in the distant past. But the extreme heat has modified these features, softening their edges, possibly partially melting the rock in the impact zones. Some craters appear filled with smooth, dark material, possibly impact melt that never completely resolidified, or volcanic material that welled up from below to fill the depressions. The geological history of TRAPPIST-1b remains difficult to read under these conditions. Heat and radiation, erasing or modifying evidence that would be preserved on cooler worlds. The extreme environment creating unique features not found elsewhere in the system. Moving toward the terminator region where the star approaches the horizon and temperatures should drop somewhat, you traverse several hundred meters of scorched terrain, passing areas where the rock shows different textures and colors. Some stone appears almost black, carbon-rich perhaps, or just darkened by extreme heating, while other areas show lighter grey, possibly different mineral compositions, or less thermally altered material. The surface is ancient, this much is clear from the cratering, and the lack of fresh features, but determining exact ages, or geological sequences, requires more detailed analysis than visual observation can provide. The terminator zone on TRAPPIST-1b offers slight relief from the intense heat, the temperature dropping to around 300 Celsius, where the star sits low on the horizon. Still extreme, but measurably cooler than the subsolar inferno. The light takes on an even deeper red quality at this grazing angle, though the brightness remains high due to the star's proximity. Looking along the terminator, the boundary between day and night, you see the landscape disappear into shadow, where the night side begins. The darkness there lit only by heat radiation from the ground itself, the rock glowing dull red in the infrared from its thermal energy. Crossing into the night side requires heat-resistant equipment to handle the initial temperatures, but moving deeper into the darkness reveals a gradual cooling as distance from the day side increases. The night hemisphere of TRAPPIST-1b is not cold like the night sides of outer planets. The heat from the day side conducts through the planet's interior and radiates from the night side rock, maintaining temperatures around 200 Celsius, even in permanent darkness. The ground glows faintly in infrared, visible with the suit's thermal imaging, the heat creating an eerie landscape of warm rock under cold stars. A world that cannot cool completely because the day side continuously feeds it energy. Looking up from the night side, the stars appear brilliant and clear, no atmospheric scattering or light pollution to dim them. The Milky Way arching overhead in glorious detail. The other planets of the TRAPPIST-1 system hang in the sky, appearing larger and more visible from the night hemisphere than from the day side, where the stars' glare overwhelmed their light. TRAPPIST-1c appears as the largest and brightest, its orbit just beyond TRAPPIST-1b, making it a prominent feature in the night sky. The habitable zone planets, TRAPPIST-1d, E, and F, cluster together at a greater distance, their positions creating a small group of disks showing various phases. The outermost planets, TRAPPIST-1g and H, appear smaller and dimmer, visible but less prominent than the inner and middle worlds. The temperature on the night side stabilizes around 150 to 200 Celsius, depending on location, still far too hot for any known biology, still hot enough to boil water if water existed here. The rock beneath your boots radiates this heat continuously, energy that has traveled through the planet, from the day side or up from the interior if any tidal heating warms this world's core. Walking in the darkness, illuminated by starlight and suit lights and the faint infrared glow of the ground, you complete the exploration of TRAPPIST-1b, understanding this world as a place of extremes, a planet where the star's proximity creates conditions found nowhere else in the system. TRAPPIST-1b represents the inner boundary of planetary existence in this system, the closest orbit where a stable world can persist against tidal forces and stellar radiation, a scorched laboratory for understanding how planets survive in extreme conditions. No life could exist here. No water remains. No atmosphere protects the surface from radiation and particle bombardment from the nearby star. Yet this world persists, has persisted for billions of years, will persist for billions more, a testament to the durability of rock and the patient stability of orbital mechanics. As you return to the spacecraft for departure, TRAPPIST-1b continues its rapid orbit, completing another year in the time it takes Earth to rotate 1.5 times, forever locked in its close dance with the red dwarf. The instruments record data throughout the visit: temperature profiles, surface composition spectroscopy, radiation measurements, all contributing to understanding how planets behave at the inner edge of stellar systems. The knowledge gained here applies not just to TRAPPIST-1b, but to thousands of similar planets orbiting red dwarf stars throughout the galaxy. Worlds discovered by transit observations from Earth, but never visited. Their conditions inferred from models now tested against direct observation. TRAPPIST-1b has shown itself, as predicted, scorched and airless. But the details, the glassy rock, and the thermal variations, and the faint glow of the night side, these could only be known by coming here, by standing on this impossible surface, under the enormous red sun. Moving outward from the innermost inferno of TRAPPIST-1b, the spacecraft climbs just slightly to reach TRAPPIST-1c, the second planet, orbiting at a distance still extremely close to the star, but measurably farther than its inner sibling. The journey between these nearest worlds takes almost no time. The tight spacing allowing transfers measured in hours rather than days. The proximity of orbits creating a neighborhood of planets rather than the vast isolation characterizing the spacing between planets in our solar system. TRAPPIST-1c appears ahead, similar in size to TRAPPIST-1b at about 110% of Earth's radius, but orbiting farther out, with a year lasting 2.4 Earth days instead of 1.5. Landing on TRAPPIST-1c's dayside, you immediately notice the slightly reduced heat compared to the innermost world. Temperature readings around 300 to 350 Celsius, rather than over 400. The star appears slightly smaller in the sky from this farther vantage point. Though the difference is subtle, the disk still enormous and dominating overhead, still blazing with red-orange light that bathes the landscape in intense illumination. The surface shows similar characteristics to TRAPPIST-1b: dark volcanic rock baked by stellar radiation, no atmosphere, no water, a world stripped to bare stone and metal by proximity to the star and by billions of years of stellar wind erosion. The landscape here preserves geological features better than the innermost planet. The slightly lower temperatures allowing rock to remain fully solid rather than approaching melting point. Surface formations maintaining their structure over geological time rather than softening and deforming. Ancient lava flows are clearly visible, frozen rivers of stone that once flowed molten across this surface billions of years ago when the planet was young and geologically active. The flows stack upon each other in layered sequences, each flow representing a separate eruption, the layers creating a record of volcanic history that could be read by experienced geologists. Whether TRAPPIST-1c remains volcanically active today is unknown. No fresh flows visible from the landing site, but the planet's interior might still harbor heat sufficient to drive occasional eruptions. Walking across the surface, you notice the texture of the rock differs subtly from TRAPPIST-1b, less glassy, more crystalline. The cooler conditions allowing minerals to form proper crystal structures as lava cooled rather than freezing into glass. The stone appears dark grey to black with occasional lighter patches, where different minerals concentrate, creating a mottled appearance across the landscape. Impact craters mark the surface in scattered locations, their preservation better here than on the hotter inner planet, rims and walls maintaining sharper definition, ejecta patterns still visible around the larger impacts. The craters suggest this world, like all planets, has been bombarded by debris throughout its history, each impact adding energy and sometimes material to the planetary surface. The star's light remains intense, creating sharp shadows where surface features block the direct rays. The contrast between illuminated and shadowed areas extreme in the airless or nearly airless environment. One large crater, visible from the landing site, casts a shadow across its interior, the darkness inside the crater protecting the floor from direct heating, possibly creating a region cooler than the surrounding sun-baked terrain. Walking toward this crater to investigate, you cross several hundred meters of rough volcanic ground, the surface more uneven than TRAPPIST-1b showed, preserving the original texture of cooled lava flows rather than being smoothed by thermal stress and partial melting. Reaching the crater rim, you look down into the shadowed interior, seeing rock perhaps 50 degrees Celsius cooler than the sunlit surroundings based on thermal imaging, still hot but noticeably less extreme. The crater measures perhaps 200 meters across and 30 meters deep, a moderate-sized impact feature probably created billions of years ago during the early bombardment phase, when the TRAPPIST-1 system cleared its debris. The floor shows accumulated fine material, dust or small rock fragments that have settled there over time, possibly material that sublimated from sun-facing surfaces and condensed in the permanent shadow of the crater interior. The walls display layering, impact having excavated through multiple lava flows to expose their edges in the crater's sides. Descending into the crater, moving into the cooler, shadowed environment, provides welcome relief from the intense surface temperature. The difference creating a microclimate of sorts within this small depression. The floor material crunches under your boots, loose particles compacting under weight, creating footprints that mark the dust. Examining the material more closely reveals tiny rock fragments and what might be glass beads. The latter formed when impact heat melted rock and sprayed it into droplets that cooled into spherical shapes before landing. Such impact glass is common on airless bodies in our solar system, found extensively on the Moon and on asteroids, and its presence here confirms the same processes operate in this distant system. Looking up from the crater floor, the star appears partially blocked by the crater rim, the reduction in direct radiation making the environment more tolerable for extended observation. Other planets should be visible in the sky, even from this shadowed location, and searching the dark expanse you locate. What must be TRAPPIST-1d, showing as a small disk near the star's position, perhaps 1/3 illuminated from this viewing angle. The outer planets are harder to identify against the star's scattered light, but patient observation reveals at least 2 more disks at greater angular distance from the stellar glare, probably TRAPPIST-1e and F, showing various phases. Climbing out of the crater, back into the full sunlight, the heat returns immediately, temperature rising 30 or 40 degrees in seconds as you move from shadow to light. The transition sharp in the absence of atmosphere to diffuse the energy. This dramatic temperature change must stress the rock, causing expansion and contraction that creates cracks and eventually breaks stone into smaller pieces. A weathering process operating on TRAPPIST-1c, and all airless bodies. Over billions of years, this thermal cycling grinds rock into dust, slowly covering surfaces with the fine material seen in the crater and in patches across the landscape wherever it can accumulate in sheltered spots. Moving toward the Terminator region to complete the exploration of TRAPPIST-1c, you traverse a landscape showing increasing evidence of ancient volcanic activity. Several features that might be volcanic vents or collapsed lava tubes appearing in the terrain ahead. One feature in particular draws attention: a pit perhaps 50 meters across, with steep walls dropping into darkness, possibly an opening into a lava tube network underground. Approaching carefully, you look into the pit and see that it descends at least 20 or 30 meters before the shadows become too deep to penetrate visually. Thermal imaging shows the interior is slightly cooler than the surface, protected from direct sunlight, possibly extending deep underground into regions that never experienced direct stellar heating. Lava tubes, if they exist here, might provide the most habitable environments on TRAPPIST-1c, protected from radiation and temperature extremes, stable in temperature compared to the surface, potentially allowing exploration of the subsurface where conditions differ dramatically from the harsh dayside. Future missions might investigate such features, sending robotic probes into the darkness to map tube networks and assess whether subsurface environments on these hot inner planets offer opportunities for scientific stations or resource extraction, despite the surface hostility. For now, the pit remains unexplored, a window into the planet's interior that hints at complexity beneath the simple surface appearance. The Terminator zone approaches as the star lowers toward the horizon ahead, its disk beginning to touch the edge of the world as you walk westward. The temperature drops noticeably with each kilometer, falling below 300 Celsius, continuing down towards 250 as the sunlight angle becomes more oblique. The quality of light shifts toward deeper red, the familiar twilight effect of low-angle illumination filtering through more distance and creating the colors associated with sunset or sunrise on Earth. Though here the sun will never complete its setting, hanging eternally at the Terminator boundary for any observer who remains at that fixed location. Crossing into the night side reveals the same pattern seen on TRAPPIST-1b. Continuing warmth from conducted heat, keeping the night hemisphere far hotter than the outer planet's night sides. Despite being in permanent darkness, temperature stabilizes around 120 to 150 Celsius on the night side. Hot enough to preclude any volatiles, hot enough that rock glows faintly in deep infrared, visible to thermal sensors as a dull emission. The ground radiates heat continuously, energy slowly leaking to space from this perpetually warm hemisphere. The heat supplied constantly from the baked dayside, just a few thousand kilometers away around the planet's circumference. Stars overhead shine clearly and brilliantly. The Milky Way spectacular in the absence of any light pollution or atmospheric scattering. Other planets visible showing their phases and positions in the complex orbital dance. TRAPPIST-1b appears as a bright crescent near where the star sits below the horizon, its orbit inside TRAPPIST-1c's, making it appear always near the star from this vantage point. The habitable zone planets cluster at greater angular distance, appearing as a group of 3 or 4 disks, depending on how many are above the horizon at this moment. their orbital positions constantly changing the view. The outermost worlds, TRAPPIST-1G and H, appear small and dim, requiring careful observation to locate against the background stars. But they complete the family of 7 worlds visible from this second planet's night hemisphere. The exploration of TRAPPIST-1C concludes, this world having shown itself as slightly less extreme than TRAPPIST-1b, but still far too hot for life or liquid water, still stripped of atmosphere, still locked in permanent day and night hemispheres, with heat dominating the conditions. The rock, the craters, the possible lava tubes, the ancient volcanic flows, all tell stories of this world's history. A geologically interesting planet despite its hostile current state. As the spacecraft lifts away for the journey to the outermost world, TRAPPIST-1C remains behind, orbiting its 2.4-day year endlessly, the second world in a system of 7, a hot neighbor to its even hotter inner sibling. The journey outward beckons. One final world awaits in this exploration of the TRAPPIST-1 system, the frozen frontier planet TRAPPIST-1H that orbits at the edge of the known system, colder and more distant than any planet yet visited. Completing the tour from scorched inner worlds through habitable zone planets to frozen outer realms, the spacecraft turns away from the star's heat, climbing out of the inner system, bound for the cold darkness of the outermost orbit. The spacecraft journeys outward from the hot inner worlds, passing through the orbits of the habitable zone planets previously explored, climbing the gravity well toward the edge of the TRAPPIST-1 system, where the 7th and final known planet circles the red dwarf star. TRAPPIST-1H appears ahead gradually, a small world orbiting at the greatest distance from the star. Taking 18.8 Earth days to complete one orbit, compared to the rapid 1.5-day year of innermost TRAPPIST-1b. The star shrinks in the viewport as distance increases, becoming smaller and dimmer, its light weakening with the square of distance according to the physics that governs all radiation spreading through space. Landing on TRAPPIST-1H's dayside brings you to the coldest world in the system. Temperature readings showing minus 130 Celsius, even at the subsolar point where sunlight strikes most directly. The star appears as a small red disk in the sky, noticeably smaller than from any previous landing. Bright enough to see clearly, but dim enough that it resembles a very bright star, rather than the brilliant sun visible from inner planets. The light this star provides at this distance barely warms the surface at all. The radiant energy too weak and too spread out to raise temperatures above the deep cold of interplanetary space. Ice covers absolutely everything visible. Thick white frost extending to every horizon, a frozen world where water has condensed and frozen into permanent deposits. Stepping onto the surface, your boots sink several centimeters into the thick powdery frost before reaching firmer ice underneath. The surface layer, possibly fresh deposits of water, sublimating and condensing in cycles, even at these extreme temperatures. The gravity feels noticeably lighter than on the larger planets. TRAPPIST-1H being smaller at about 76% of Earth's radius. The smallest planet in the system you have visited, and the only one with obviously reduced gravity compared to Earth. Moving across the ice feels different in this lighter pull. Each step carrying you farther, the reduced weight making the thick frost less of an impediment to walking. The landscape shows gentle, rolling terrain, all features smoothed and softened by the thick ice covering. No bare rock visible anywhere from this vantage point. The ice might be kilometers deep here, accumulated over billions of years, as any atmosphere this world once possessed, condensed and froze onto the permanent night side, leaving perhaps just traces of gas on the cold dayside and none at all in the frozen night hemisphere. Whether TRAPPIST-1H ever had significant atmosphere remains uncertain, the planet's small size and low gravity making atmospheric retention challenging even without stellar wind stripping. But the abundance of ice suggests water existed here in large quantities throughout this world's history. Looking up at the sky, you see darkness approaching the black of space, even though the sun shines. The combination of extreme distance, weak illumination, and absent or minimal atmosphere, creating conditions where stars are clearly visible during the daytime. The Milky Way appears as a bright band arching across the sky. Thousands of stars scattered across the view. The galaxy's structure, visible in detail, rarely seen except from the darkest locations. This outer vantage point provides the best view of stars of any location in the TRAPPIST-1 system, the bright inner planets and their nearby star not overwhelming the sky, allowing the broader universe to show itself. All 6 inner sibling planets are visible from here, clustered together near the small red star, like a family huddled around a dim fire, their orbital positions creating a group of disks showing various phases and sizes, depending on their distance from this outermost world. TRAPPIST-1G appears as the largest and closest, its orbit just inside TRAPPIST-1H's, making it a prominent feature in the sky, showing perhaps half of its disk illuminated from this viewing angle. TRAPPIST-1F and E, the habitable zone worlds, appear smaller and closer to the star, their phases creating crescents or partial disks that change slowly as all 7 planets wheel through their complex orbital dance. TRAPPIST-1D, C, and B cluster even tighter around the star, their inner orbits making them appear as a tight group, difficult to separate individually without careful observation or telescopic aid. The view of all 6 siblings visible at once from this outer vantage point emphasizes the compact nature of the TRAPPIST-1 system. All 7 planets orbiting within a space that would fit inside Mercury's orbit around our Sun, a miniature planetary system compressed into a region that seems impossibly small by the standards of our home solar system. From Earth, Mercury orbits at about 0.39 astronomical units from the Sun. Yet here, at TRAPPIST-1H, you orbit at only 0.062 astronomical units from the star and stand at the outer edge of the known system. The compression of this system into such tight quarters results from the star's small size and low mass, its weaker gravity, requiring planets to orbit much closer to achieve the same orbital periods and dynamics that larger stars create at greater distances. Everything here is scaled down, miniaturized. A pocket solar system where interplanetary distances that would take spacecraft months to cross in our system require only days or weeks of travel. The frozen surface stretches outward in every direction, and walking across it, you notice features that might be impact craters, circular depressions in the ice, partially filled with drifted frost, marking places where ancient meteorites struck this small world. The craters appear well preserved, their rims still sharp in places, despite the smoothing effect of ice suggesting this surface might be ancient, undisturbed by geological activity for billions of years. Small worlds like TRAPPIST-1 cool rapidly after formation, their interiors losing heat quickly due to the unfavorable ratio of volume to surface area. And geological activity likely ceased here long ago, leaving a cold, dead interior beneath the frozen crust. Any craters that formed since the surface froze would remain largely unchanged, preserving a record of impacts spanning much of this planet's history. Temperature sensors show that even within a few meters of altitude above the surface, the temperature drops further. The thin layer of any remaining atmosphere, unable to trap or distribute heat effectively across the planet. If atmosphere exists here at all, it might consist of just traces of nitrogen or carbon dioxide, gases that remain gaseous even at these extreme temperatures, though most likely any substantial atmosphere collapsed and froze onto the night side billions of years ago. The dayside maintains temperature just barely above what thermodynamics would predict for bare rock at this distance from the star, suggesting perhaps the tiniest presence of greenhouse gases or atmospheric remnants warming the surface by a few degrees. Moving toward the terminator, the line separating eternal day from eternal night, you notice the temperature dropping even from the already extreme cold. The sun lowering toward the horizon as you walk away from the subsolar point. The terminator on TRAPPIST-1 H offers no temperate zone, no comfortable band where conditions moderate between the day and night extremes. Just a gradient from extremely cold to even colder as sunlight disappears entirely. The landscape darkens as you approach, the dim red light fading, long shadows from small ice ridges and crater rims stretching across the frozen ground, creating patterns of light and dark. At the terminator, the star sits on the horizon, half of its small red disk visible above the ice plain, providing almost no warmth at all from this low angle. The light passing through whatever thin atmosphere might exist at a shallow angle that scatters and dims it further. The view from here shows the dayside behind you, dimly illuminated in red, and the night side ahead, completely dark except for the brilliant stars overhead. Temperature readings show minus 150 Celsius, the loss of even the minimal direct sunlight causing conditions to worsen. And you wonder how much colder the deep night side becomes, where no sunlight has touched the surface for billions of years. Crossing into the night side brings absolute darkness and cold that reaches toward the theoretical minimum temperature this world can achieve, limited only by the faint heat radiating from the planet's small warm core and the minute amount of starlight and infrared radiation from the distant star. The temperature drops to minus 170 Celsius, approaching the freezing point of nitrogen, if any nitrogen exists here. Cold enough that carbon dioxide would be solid ice, and oxygen would be a liquid if present in significant quantities. Your suit systems work harder to maintain comfortable temperature inside, the heating elements counteracting the extreme cold, trying to leach warmth away through radiation and conduction, where the boots contact the frozen ground. The ice beneath your feet is rock hard at these temperatures, all mechanical properties of water ice, enhanced by the extreme cold, making it more like stone than anything resembling snow or frost. You could be walking on solid rock for all the difference the surface texture provides. The ice compressed and frozen so thoroughly that it has become a geological material in its own right, forming the permanent crust of this frozen world. Beneath this ice layer might lie more ice extending kilometers down, or perhaps rock appears at some depth, the original surface of the planet buried under accumulated frozen volatiles. But from here, the ice seems endless. Looking up from the night side, the sky blazes with stars, the darkness complete, except for the brilliant points of light scattered across the heavens. No scattered sunlight or atmospheric glow to diminish their clarity. The Milky Way appears as a bright river of light flowing across the sky, individual stars resolved within it, nebulae and dark lanes visible to the unaided eye in detail that would require dark skies and patience to observe from Earth. Spending time in this darkness allows your eyes to adjust fully, and the number of visible stars seems to increase until the sky appears almost crowded with them. Thousands upon thousands of distant suns, each marking a place in the galaxy. The 6 inner planets shine in the sky, near the horizon, where the star sits just below the rim, their reflected starlight making them visible as crescents and partial disks. Tiny moons in the darkness, marking the locations of your sibling worlds. TRAPPIST-1G appears brightest and largest, its proximity and size making it prominent even in crescent phase, a small arc of light hanging in the black sky. The habitable zone worlds appear smaller. TRAPPIST-1E and F showing as tiny crescents, barely distinguishable from bright stars, except for their positions and the fact that they show phases rather than appearing as point sources. The inner hot worlds cluster tightly, TRAPPIST-1B, C and D forming a small group near where the star hides below the horizon, their phases showing them as thin crescents, since you view them from the outer system looking inward toward the star. The silence here feels absolute. No wind to create sound, no atmosphere to carry vibrations, no geological activity to rumble in the deep. Just the perfect quiet of a frozen world that has been still for billions of years and will remain still for billions more. Standing motionless, you become part of that stillness, another cold object on the surface of TRAPPIST-1H, and the peace of it settles into your awareness. The calm of a place where nothing changes and nothing will change for timescales beyond human comprehension. This outermost world represents the end of the system, the final planet known to orbit TRAPPIST-1. The boundary between the planetary realm and the empty space beyond, where perhaps other objects drift, but where no large planets have been detected. Whether additional planets exist beyond TRAPPIST-1H remains unknown. Observations from Earth and transit timing variations have not revealed any additional worlds, but cannot rule out their existence, especially if such planets orbit farther out or at angles that prevent them from transiting the star, as seen from Earth. The methods that discovered these 7 worlds work best for planets that cross between Earth and their star, blocking tiny fractions of starlight in regular patterns that reveal their presence. But planets that do not transit remain invisible to this technique. Other methods like radial velocity measurements or direct imaging might someday reveal additional worlds. Or this might be the complete roster. 7 planets from innermost scorched TRAPPIST-1B to outermost frozen TRAPPIST-1H, with nothing beyond but cold, empty space. Looking outward from the night side, away from the star and away from the 6 visible sibling planets, you see only stars and darkness. The deep black of interstellar space, extending infinitely in that direction. A reminder that this system, is just one small corner of a galaxy containing hundreds of billions of stars and an estimated trillions of planets. Each star visible in the sky might have its own system, its own collection of worlds, some perhaps similar to this compact arrangement, others spread out like our solar system, and still others in configurations not represented in either system. The statistical likelihood suggests that planetary systems are common, perhaps nearly universal, around stable stars, and the diversity of architectures probably exceeds our current ability to observe or imagine. Your time on TRAPPIST-1, H draws toward conclusion, the exploration of this frozen frontier complete, the experience of standing on the outermost edge of this remarkable system, stored in memory and instrumentation. You have now walked on all 7 worlds that orbit TRAPPIST-1, from the scorching heat of TRAPPIST-1b, where rock might still be molten in places, through the potentially habitable TRAPPIST-1e and f, where temperatures allow liquid water and the warmth of red sunlight feels almost comfortable, to this frozen outer world where cold reigns supreme and ice covers everything. Each planet held its own character, its own particular combination of temperature, light, ice, and rock that made it distinct despite the overall similarity in size and composition. And seeing them all provides perspective on how position and distance from a star shape the conditions and possibilities for each world. The journey continues now, leaving the individual planets behind to view the system as a whole, to see the orbital mechanics and transits that make TRAPPIST-1 scientifically valuable and visually spectacular from the right vantage points. The spacecraft lifts from the frozen surface of TRAPPIST-1H, ascending through the minimal atmosphere or complete vacuum, depending on what remains here, climbing away from the ice and out into the space between planets, where the full architecture of the system becomes visible. Behind you, TRAPPIST-1H recedes, becoming smaller, joining its 6 siblings as objects in the sky, rather than ground beneath your feet. And ahead, the complex dance of 7 worlds around a red dwarf star waits to be witnessed. The spacecraft positions itself above the orbital plane of the TRAPPIST-1 system, rising perpendicular to the flat disk where all 7 planets circle the star. Reaching a vantage point where the architecture of the entire system becomes visible at once, like a diagram brought to life. From this elevated position, the 7 planetary orbits appear as concentric rings around the red dwarf star, each planet moving along its circular or nearly circular path at different speeds. The inner worlds racing along, while the outer planets proceed at more leisurely paces. The star sits at the center, a small red sphere glowing dimly compared to larger stars, but brilliant against the darkness of space, its light spreading outward to illuminate the orbiting worlds in diminishing amounts as distance increases. TRAPPIST-1b, the innermost planet, orbits so rapidly that you can see its motion clearly, the planet visibly moving against the background of stars and the more distant planets, completing 1 full orbit every 36 hours. Its position changes noticeably over the course of just minutes, the small world racing around the star, forever locked with one face toward the star and one facing away, spinning on its axis exactly once per orbit to maintain that tidal lock. Watching it move provides a tangible sense of orbital mechanics in action, the planet following the path that gravity and velocity dictate. neither falling into the star nor flying away into space, but maintaining the perfect balance that defines a stable orbit. TRAPPIST-1c follows in the next orbit outward, moving more slowly at 2.4-day orbital period. Its path slightly larger than TRAPPIST-1b's, but still tight around the small star. The two inner planets appear to chase each other around the star, TRAPPIST-1b faster, and occasionally passing TRAPPIST-1c when their orbits bring them into alignment on the same side of the star. These passing configurations happen regularly, the mathematical relationship between their orbital periods creating a resonance where they align in the same configuration every few orbits. The gravitational influences they exert on each other during these close approaches, helping to maintain the stability of their orbits over billions of years. TRAPPIST-1d occupies the third orbit, its 4-day period, placing it just at the inner edge of the habitable zone. And from this overhead view, you can see its position relative to the other planets change hour by hour as all 7 worlds move through their complex choreography. The compact spacing means that conjunctions and alignments happen frequently, planets lining up on the same side of the star multiple times per month, creating configurations where 3, 4, or even all 7 planets arrange themselves in a line extending outward from the star. These alignments have scientific value. The gravitational interactions between planets during close configurations, revealing information about their masses and orbital parameters through tiny variations in their transit timing. The 3 habitable zone planets, TRAPPIST-1d, E, and F, orbit in the middle region of the system, where temperatures allow the possibility of liquid water and stable surface conditions. Their paths spaced close enough that they frequently pass near each other in their orbital dance. TRAPPIST-1e, the most Earth-like world, orbits with a 6-day period, moving at a moderate pace that seems sedate compared to the inner worlds, but still rapid by the standards of our solar system, where Earth takes 365 days to orbit the Sun. TRAPPIST-1 fells with its 9-day orbit, and watching these 2 planets move reveals the 3-to-2 resonance they share. TRAPPIST-1e completing exactly 3 orbits in the time. TRAPPIST-1f completes 2. A mathematical relationship that creates regular close approaches and helps stabilize both orbits. TRAPPIST-1g occupies the 6th orbit at 12.4-day period, moving slowly enough that its motion requires patient observation to detect, and TRAPPIST-1h traces the outermost known path at 18.8 days, its position changing almost imperceptibly compared to the racing inner planets. The 7 orbits together create a nested structure, each ring containing a planet, each planet moving at the speed dictated by its distance from the star and the physics of gravity. The whole system displaying an elegance of organization that seems almost designed, despite being entirely the product of natural processes. The orbital resonances that connect many of these planets emerged naturally from gravitational interactions during the system's formation, planets migrating inward or outward until they settled into stable configurations where their periods relate through simple ratios. Watching the system from above, you begin to notice patterns in the motion, the way certain planets seem to return to similar configurations repeatedly, the resonances creating periodicity in the chaos of 7 bodies moving under mutual gravitational influence. TRAPPIST-1, B, C, and D share resonances that link their orbits, as do the triplet of TRAPPIST-1e, F and G, creating two groups of planets whose motions synchronize through gravitational choreography. These resonances prevent close approaches that might destabilize orbits. The timing arranged such that when planets come near each other, they always do so at the same points in their orbits, creating predictable perturbations rather than random gravitational chaos. The spacecraft moves to align itself with the orbital plane, descending back into the disk where the planets orbit, positioning to observe the transits that make this system famous and scientifically valuable. A transit occurs when a planet passes directly between the observer and the star, the planet's disk blocking a tiny fraction of the star's light, creating a measurable dimming that reveals the planet's size and orbital period. From Earth, astronomers discovered all 7 TRAPPIST-1 planets by watching these transits, the regular dips in the star's brightness indicating planets crossing the star's face. And from within the system, the transits become dramatic visual events, rather than just photometric data. You are listening to the Drowsy Astronaut, and tonight we drift together through the TRAPPIST-1 system, watching 7 worlds dance in their compact orbits around a red dwarf star, 40 light-years from home. We move slowly through this experience, taking time to see what each planet offers, understanding how they move and interact, witnessing the transits and alignments that make this system unique. If you are finding peace in this journey, a like or subscription helps us continue creating these slow explorations. And if you are listening from somewhere on Earth, you might share where you are in the comments, connecting with others who find calm in cosmic wandering. The view ahead shows TRAPPIST-1e approaching a transit, the planet moving toward alignment with the star as seen from this position, preparing to cross the red dwarf's face. The planet TRAPPIST-1e moves closer to the star's disk, approaching from the right side of the star, as seen from your position. Its motion bringing it toward the moment of first contact, when its dark outline will touch the star's edge. The star appears as a red circle, its brightness moderate, its surface showing the granulation and convection patterns common to red dwarf stars, darker and lighter patches where heat rises and falls in the outer layers. TRAPPIST-1e appears as a dark circle against the background stars, not yet overlapping the star. Its size similar to Earth's, making it appear relatively small compared to the star's disk, despite the star being much smaller than our Sun. First contact occurs when the edge of TRAPPIST-1e's disk touches the edge of the star's disk, the dark circle beginning to overlap the red circle, creating a small notch in the star's outline that deepens as the planet continues moving. The dimming of starlight begins immediately. The fraction of light blocked proportional to the fraction of the star's disk covered by the planet, and instruments would register the decrease, even though the change appears subtle to the eye. The planet's dark disk stands out sharply against the red star. No atmosphere visible around its limb. No haze or glow softening the edge. Just the clean, circular shadow of a rocky world passing across a distant sun. The transit continues as TRAPPIST-1e moves fully onto the star's disk, the entire circular outline of the planet, visible as a dark spot against the red background, and you watch it slowly cross from right to left, taking several hours to complete the passage. The size comparison becomes clear during the transit, the planet measuring about 92% of Earth's diameter, while the star measures only about 12% of the Sun's diameter, making the ratio of planet size to star size much larger than Earth to Sun ratios and causing more significant dimming during transits. If you could observe this transit from Earth, instruments would detect about a 1% drop in the star's brightness, a substantial signal that makes these planets relatively easy to detect, despite their small sizes and great distance. Watching the transit from this close vantage point provides perspective that numbers and diagrams cannot fully convey, the reality of a world crossing between you and its star. The physical geometry of the solar system made visible through direct observation, rather than inferred from data. The planet continues its slow march across the star's face, and you notice other planets visible in the surrounding space. TRAPPIST-1 F off to one side, TRAPPIST-1 D on the other, both showing phases, their positions in their own orbits determining how much of their daysides are visible from this location. As TRAPPIST-1 E approaches the center of the star's disk, you notice another dark circle appearing at the star's right edge, a second planet beginning its own transit. And checking positions confirms that TRAPPIST-1D has aligned for a transit at the same time, creating a rare double transit where two planets cross the star simultaneously. The two dark circles on the red star create a striking image, two worlds separated by millions of kilometers in space, but appearing close together on the star's face from this viewing angle. Their different sizes apparent, with TRAPPIST-1D being smaller than TRAPPIST-1E and therefore blocking less light. The double transit continues, with both planets visible against the star, moving at different speeds due to their different orbital velocities. TRAPPIST-1D moving faster because it orbits closer to the star, where orbital speed must be higher to counteract the stronger gravitational pull. The faster inner planet gradually catches up to the slower outer planet. As both cross the star, the spacing between the two dark circles decreasing, as TRAPPIST-1D approaches TRAPPIST-1E from behind. For a brief period, the two planets nearly overlap from this viewing angle, their dark circles almost touching on the star's face, though in reality, they remain separated by the substantial distance between their orbital radii. Third contact for TRAPPIST-1E occurs when the planet's trailing edge reaches the star's far edge, the dark circle beginning to move off the red disk, and the transit enters its final phase as the planet slowly clears the star's limb. The dimming lessens as more of the star becomes visible again, the light increasing back toward its full brightness, and within minutes, TRAPPIST-1E completes its transit, moving entirely off the star and returning to being just another dark circle against the background stars. TRAPPIST-1D continues its transit, still crossing the star's face, and you watch it proceed, knowing that somewhere behind you, TRAPPIST-1C or B might be starting their own transits. The geometry of 7 planets orbiting in nearly the same plane, creating frequent opportunities for these crossings. The frequency of transits in the TRAPPIST-1 system far exceeds what any observer of our solar system would experience. The combination of short orbital periods and multiple planets creating events almost daily where some planet crosses the star. From any given vantage point within the system, transits occur regularly, providing constant reminders of the orbital motion and planetary presence. The system never allowing long periods of quiet where nothing moves or changes. The resonances ensure that certain combinations of planets transit together at predictable intervals. Double and triple transits happening periodically as the orbital choreography brings multiple worlds into alignment. Moving the spacecraft to different positions in the system reveals how transit visibility depends on viewing angle. Transit's only visible when the observer, planet, and star align closely enough for the planet to pass between the other two. From positions above or below the orbital plane, transits never occur, the planets passing above or below the star's disk from those viewing angles, and this geometric requirement explains why Earth-based observers can see these transits at all. Our solar system happening to align with the TRAPPIST-1 orbital plane within the narrow angle required for transits to occur. If Earth orbited at a different location in space, tilted relative to TRAPPIST-1's orbital plane, we might never have detected these planets through the transit method, the stars appearing constant in brightness, as planets orbited unseen, passing beside rather than in front of their star. The view from within the system provides opportunities impossible from Earth, positioning spacecraft at any angle to observe transits, alignments, conjunctions, and orbital configurations from perspectives that reveal the three-dimensional structure of the system rather than just the two-dimensional projection visible from 40 light-years away. You could watch planets transit each other rather than just the star, one planet passing in front of another from certain viewing angles, or observe how moons, if any of these planets have moons, would transit both their parent planet and a star in complex patterns determined by the moon's orbit around the planet and the planet's orbit around the star. The spacecraft moves outward from the close confines of the planetary orbits, climbing away from TRAPPIST-1 and its family of 7 worlds, ascending through the empty space beyond the outermost planet's orbit toward a vantage point where the star system becomes just one object among many, rather than the dominant presence filling the entire sky. The red dwarf star shrinks as distance increases, becoming smaller and dimmer, and the planets fade from visibility one by one as their faint reflected light becomes too dim to see against the darkness of space. The system recedes behind you, becoming a memory and a collection of instrument readings, while ahead the broader universe reveals itself, the galaxy spreading across the view in all its ancient glory. The Milky Way dominates the sky, a river of light flowing from one horizon to the other, its band brightest toward the galactic core, though that core lies too far away to see as anything other than a bright concentration of distant stars. Thousands of individual stars scatter across the view, each one a sun, each one potentially hosting planets of its own, each one representing a destination that spacecraft from Earth might someday reach, if technology and determination permit such journeys. The stars appear in various colors: blue-white giants burning hot and fast, yellow stars like our sun in the middle of their lives, red dwarfs like TRAPPIST-1 that will burn for trillions of years, each color telling something about the star's temperature, size, and age. Looking toward the direction of Earth's location in space, you search the star field for Sol, our sun, knowing it should be visible from this distance, but uncertain which point of light among thousands represents home. The constellations appear mostly familiar, despite the 40 light-year displacement, the stars being so far apart that shifting perspective by 40 light-years changes apparent positions only slightly for most of them. Orion still looks like Orion. The Big Dipper maintains its shape. The patterns that humans have recognized for millennia persisting across interstellar distances. Though careful observation would reveal subtle shifts in star positions, parallax effects created by the change in viewing angle. Using navigation instruments, you locate Sol, the star appearing as a modest yellow-white point in the constellation Aquarius, as seen from here. Unremarkable among the countless other stars, except for the significance it holds as home. The Sun looks ordinary from 40 light-years away. Neither particularly bright, nor particularly dim, neither notably colourful, nor unusually positioned. Just one more star in a galaxy that contains 200 billion stars or more. Knowing that Earth orbits that distant point creates a strange feeling, all of human history occurring on a planet circling a star that appears indistinguishable from thousands of others visible in this sky. Our entire civilization reduced to an invisible speck near an average star. The light you see from Sol left that star 40 years ago, traveled through interstellar space at the constant speed of 300,000 kilometers per second, and arrived at your eyes here, near TRAPPIST-1, on this particular night. If the light could carry information about Earth, it would show the world as it existed 40 years in the past. Whatever events and conditions prevailed, then frozen into the photons that traveled this immense distance. Similarly, the light from TRAPPIST-1 that arrives at Earth tonight left this star 40 years ago, the photons traveling the same distance in the opposite direction, creating a situation where each star sees the other as it was, decades in the past. The finite speed of light, creating a delay in information that increases with distance. Radio signals from Earth take 40 years to reach TRAPPIST-1, and any signal sent from here would take another 40 years to return to Earth, creating an 80-year round-trip communication time that makes conversation impossible and limits interaction to carefully planned messages sent without expectation of timely response. If humans at Earth transmitted a message tonight asking about conditions in the TRAPPIST-1 system, that message would not arrive here until 40 years from now, and any response sent immediately upon receiving the message would not reach Earth until 80 years after the original transmission, a delay that requires patience measured in human lifetimes. This light speed limit shapes all discussion of interstellar exploration and communication. The vast distances between stars creating not just spatial separation, but temporal isolation, where information and influence propagate slowly despite traveling at the fastest speed physics allows. Other nearby stars become identifiable through instruments and catalogues. Red dwarfs, similar to TRAPPIST-1, scattered throughout this region of space. Each one a small, cool star burning hydrogen slowly and steadily. Their dim light invisible or barely visible to Earth-based observers, but substantial when encountered at close range. Red dwarfs make up about 70% of all stars in the galaxy. Their small masses and low temperatures making them the most common stellar type. And many harbour planets, as the discoveries of recent decades have proven. TRAPPIST-1 represents just one example of this common stellar class. Its 7-planet system, perhaps unusual in having so many worlds, but not unique in having planets at all. The discovery of the TRAPPIST-1 system occurred over several months in 2016 and 2017. Astronomers using the Transiting Planets and Planetesimal Small Telescope, abbreviated TRAPPIST, to observe the star and detect the regular dimming patterns that indicated planets crossing its face. Initial observations revealed 3 planets. Further study revealed 4 more, and detailed analysis confirmed that all 7 were roughly Earth-sized, and 3 or 4 occupied the habitable zone where liquid water could potentially exist. The announcement of 7 temperate terrestrial planets around a single star created enormous scientific and public interest, the system immediately becoming a prime target for further study and for searchers for signs of life or habitable conditions. The James Webb Space Telescope and other instruments have studied the TRAPPIST-1 planets since their discovery, attempting to determine whether these worlds have atmospheres, and if so, what those atmospheres contain. Transit spectroscopy, where instruments analyze starlight filtered through a planet's atmosphere during transits, can reveal the presence of gases like water vapor, oxygen, carbon dioxide, methane, and other compounds that might indicate habitable conditions or even biological activity. Early results have been mixed, some planets showing possible signs of atmospheres, while others might be airless, the data requiring careful interpretation and additional observations to reach confident conclusions about conditions on these distant worlds. The possibility of life in the TRAPPIST-1 system remains an open question. The presence of Earth-sized planets in the habitable zone, providing the basic requirements, but many other factors influencing whether life could actually arise or persist on these worlds. Red dwarf stars produce powerful stellar flares, eruptions of energy, and charged particles that could strip away planetary atmospheres or sterilize surfaces with radiation, creating hostile conditions despite the otherwise favorable orbital distances. Tidal locking might concentrate heat on the dayside and freeze the night side, though atmospheric circulation could potentially redistribute heat if the atmosphere is thick enough, creating a narrow habitable band at the terminator, or even allowing global habitability through greenhouse effects. The statistical implications of the TRAPPIST-1 discovery extend beyond this single system. The existence of 7 Earth-sized planets around one star, suggesting that such compact, multi-planet systems might be common around red dwarfs. If the galaxy contains 200 billion stars and 70% are red dwarfs, that creates a population of about 140 billion red dwarf stars. And if even a small percentage of those host multiple Earth-sized planets in their habitable zones, the total number of potentially habitable worlds could reach into the billions. This statistical reasoning feeds into estimates of how many life-bearing planets might exist in the galaxy. The Drake equation and similar frameworks incorporating planetary abundance as a crucial factor in calculating the probability of finding life elsewhere. The search for biosignatures, chemical signs of life in planetary atmospheres, focuses on combinations of gases that would be unlikely to coexist without biological processes, maintaining them out of chemical equilibrium. Oxygen and methane together, for example, would quickly react to form carbon dioxide and water, unless something continuously replenishes them. And on Earth, that something is life, with photosynthesis producing oxygen and various microbes producing methane. Finding such combinations in a TRAPPIST-1 planet's atmosphere would not prove life exists there, but would provide compelling evidence worth investigating further, perhaps even justifying ambitious missions to study the planet more closely or search for additional confirming evidence. Looking at TRAPPIST-1 from this distance, now just a red point of light among many stars. You reflect on the system you have explored, the 7 worlds, each with their own character. Their compact arrangement creating a mini solar system where interplanetary distances are short and planets loom large in each other's skies. The experience of visiting each world, feeling the temperature differences from scorching TRAPPIST-1b to frozen TRAPPIST-1h, seeing the star change size and brightness with distance, watching the transits and orbital dance from within the system rather than from billions of kilometers away. All this creates understanding that observations and data alone cannot provide. Being there, even hypothetically, makes the system real in a way that catalog numbers and scientific papers cannot achieve. The spacecraft begins the long journey back toward Earth, though the actual travel time would span decades or centuries, depending on propulsion technology. The 40 light-years separating TRAPPIST-1 from our solar system, representing a vast gulf that current spacecraft could not cross within human lifetimes. Interstellar travel remains mostly theoretical. The energy requirements and timescales involved making trips between stars extraordinarily challenging, though concepts exist for fusion-powered spacecraft, light sails pushed by lasers, or generation ships where multiple human lifetimes pass during the journey. Perhaps someday humans or their robotic emissaries will truly visit TRAPPIST-1, walking on these planets as we have imagined tonight. But for now, the exploration remains in the realm of careful observation, from afar and detailed imagination, based on scientific understanding. The stars around you begin to shift perspective as the spacecraft accelerates, though the motion is imperceptible without checking instruments. The distance is so vast that even high speeds produce little apparent change in star positions. The view remains essentially static, TRAPPIST-1 fading behind as other stars hold their positions, the galaxy maintaining its appearance. The journey home requiring patience and time, measured in years or decades before familiar constellations would begin to look right again, and the sun would grow bright enough to appear special among the field of stars. The journey winds towards its conclusion, and rather than continue outward or race toward home, the experience settles into quiet observation, returning in mind and memory to one specific place that encapsulates the wonder of the TRAPPIST-1 system more perfectly than any other location. TRAPPIST-1E's terminator, the narrow band where eternal sunset paints the landscape in deep red twilight, calls as the ideal setting for the final moments of this exploration. The place where day and night meet, where temperature moderates between extremes, where the sky shows both the red sun and the scattered stars simultaneously. You find yourself standing once again on TRAPPIST-1E at the terminator, the position and view recreated through memory or through actually returning there. The details mattering less than the experience of being present. In this particular place, at this particular moment, the red sun sits motionless on the horizon, half its disk visible above the rocky ground, its light streaming across the landscape at a low angle that creates long shadows and paints everything in shades of amber and rust. The temperature here feels comfortable, the suit systems barely working to maintain climate control. The natural conditions at this boundary zone, falling within the range that Earth life would tolerate if such life existed here. The landscape around this terminator position shows terrain that could almost be mistaken for Earth if you ignored the color of the light and the unfamiliar sky, rocky ground scattered with stones, gentle hills rising in the distance, the geology of a terrestrial planet shaped by billions of years of whatever processes operate here. Whether water ever flowed across this surface remains uncertain. The question of current or past habitability still opened pending more data from Earth-based telescopes and possible future missions. But the landscape seems compatible with the idea, neither obviously hostile nor clearly welcoming, just quiet stone under an alien sun. Looking up, the salmon-colored sky shows other planets visible even in this twilight. TRAPPIST-1 hanging large and bright, showing a half-phase, TRAPPIST-1d, smaller and closer to the sun, showing as a crescent, other worlds scattered across the view at various positions in their orbits. The arrangement changes slowly, hour by hour, as all 7 planets continue their orbital dance. The compact system ensuring that some worlds are always visible from any given location. The family of planets never fully hidden, their presence a constant reminder that this is not a solitary world, but part of a multi-planet systems, unlike anything in our solar system's architecture. The stars begin to appear in the darker part of the sky away from the sun. The twilight dim enough that brighter stars show through. And as minutes pass, more stars emerge as your eyes adjust to the available light. The Milky Way becomes faintly visible arching across the darkening sky. Its structure subtle in the twilight, but present for patient observation. The galaxy making its presence known even here, at the edge between day and night. This view combines elements impossible to see together from most places. The sun and the stars sharing the sky, planets showing phases, while the galactic background emerges, all visible simultaneously from this unique vantage point. The silence here feels profound. No wind sounds in the thin atmosphere, if atmosphere exists. No geological rumbles from a world likely long dead, internally. No biological sounds because no evidence suggests life has ever arisen here. Just the pure quiet of stone and sky, and the patient turning of the cosmos. Sitting on a rock at this terminator, you become part of that silence, another element in the landscape, still and observant, experiencing rather than analyzing, present rather than thinking about being present, the moment sufficient unto itself, without need for interpretation or meaning, beyond what simply exists. Time passes, though how much remains unclear. The unchanging sun and the slowly shifting planets, providing the only measures of duration, and you watch TRAPPIST-1, F, move visibly across the sky, over the course of what might be hours, its position changing as it orbits, its phase shifting subtly as the geometry between your location, TRAPPIST-1F, and the star evolves. The other visible planets also move, though more slowly, their greater distances or different orbital positions making their motion harder to detect without extended observation. But patient watching reveals the changes, the system alive with motion even in its apparent stillness. The experience of having explored all 7 worlds settles into memory as you sit in this twilight, each planet distinct in your recollection. The scorching heat of TRAPPIST-1b and c, where the star dominated the sky. The comfortable warmth of TRAPPIST-1e's dayside, where the sun felt almost friendly. The deepening cold of TRAPPIST-1, F and G, where ice began to dominate the landscape. The extreme frozen conditions of TRAPPIST-1H, where the star appeared as just a bright red star barely warming the surface. Each world contributed to understanding the system as a whole. The progression from hot to cold, creating a spectrum of environments that illustrated how distance from a star shapes planetary conditions even more than the star's characteristics shape them. The scientific importance of TRAPPIST-1 lies not just in having potentially habitable planets, but in having multiple similar planets at different distances, providing a laboratory for comparative planetology where variables can be isolated and studied. How does temperature affect atmosphere retention? How does tidal locking influence climate? What role does stellar radiation play in surface chemistry? These questions can be approached by comparing the 7 TRAPPIST-1 planets, each one similar in size and composition, but different in orbital distance, and therefore different in the conditions they experience. Natural experiments created by the physics of planetary formation and orbital dynamics. The human significance extends beyond science into philosophy and perspective. The knowledge that 7 Earth-sized worlds orbit a star, 40 light-years from here, expanding our understanding of what exists in the universe and what might be possible. For most of history, humans knew only one planet, Earth, and even when astronomy revealed other planets, they were the distant giants of the outer solar system, or the small rocky worlds of the inner system. None quite like Earth in size and characteristics. The discovery of thousands of exoplanets over recent decades has shown that Earth-sized rocky planets are common, and TRAPPIST-1 has demonstrated that such planets can exist in groups around small red dwarf stars, fundamentally changing our picture of the cosmos. The possibility that life exists somewhere in this system, perhaps in the subsurface oceans of TRAPPIST-1G, if tidal heating keeps water liquid beneath an ice shell, perhaps in protected terminator regions of TRAPPIST-1E, if atmosphere distributes heat adequately, perhaps in environments we have not yet imagined, adds another layer of significance to the exploration. Discovering life beyond Earth would answer one of humanity's deepest questions, proving that biology is not unique to our world, but a general phenomenon that arises wherever conditions permit. And finding such life in the TRAPPIST-1 system would make these 7 planets even more important as subjects of study and as destinations for future exploration. The twilight deepens slightly as you continue sitting at the terminator, more stars becoming visible, the sky transitioning from salmon to darker orange-red. The sun's position unchanged, but the scattering of its light through whatever atmosphere exists here, changing the appearance of the sky. The view remains beautiful in its alien familiarity, recognizably a planetary surface under a sky, but undeniably different from Earth, in the quality of light and the presence of other worlds hanging overhead, the combination creating something new to human experience. A vista that no one from Earth has seen with their own eyes, but that might someday become as familiar as images of Mars or the Moon. The journey through the TRAPPIST-1 system ends here, at this terminator, under this red twilight, with planets visible in the sky and silence surrounding everything. The experience complete, not because everything has been seen or understood, but because the essential character of the system has been witnessed and absorbed. 7 worlds orbiting a red dwarf star, 3 or 4 of them potentially habitable, all of them tidally locked, all visible from each other's skies. The compact architecture creating a mini solar system unlike our own, but no less real, no less worthy of wonder, no less valuable for what it teaches about planets and stars and the possibilities the universe contains. Gratitude for the exploration settles in. Gratitude for the science that discovered these worlds. For the imagination that can visit them even across 40 light years. For the universe that creates such places and allows them to exist. For the simple fact that we live in a cosmos rich with worlds and possibilities beyond our immediate experience. The TRAPPIST-1 system will continue its ancient dance, whether humans observe it or not. The 7 planets orbiting their red star for billions of years into the future, possibly harboring life, possibly barren, definitely present, definitely real, definitely worth knowing about, even if we never visit them in person. The red sun sits on the horizon, unchanging, patient, eternal in its position relative to this spot on TRAPPIST-1E's surface, where the Terminator holds day and night in perfect balance. The planets drift slowly across the sky, their orbital motion continuing as it has for billions of years, and will for billions more. The stars shine in the darker portions of the sky. The Milky Way arches overhead, and the silence holds everything in its gentle embrace, the peace of a cosmic vista that asks nothing except to be witnessed, appreciated, and remembered. Sleep comes naturally in this twilight, the mind settling as the landscape settles, the day's explorations complete, the journey through 7 worlds accomplished, the experience stored in memory and imagination, where it will remain accessible whenever wonder calls and curiosity reaches toward the stars. Dreams might carry you to other worlds tonight, other systems, other vantage points in the vast universe that contains not just TRAPPIST-1's 7 planets, but trillions of worlds scattered through hundreds of billions of stars across a galaxy that itself is just one among hundreds of billions of galaxies. But for now, this Terminator on TRAPPIST-1E is enough. This view of planets and stars and red twilight sufficient. This moment of cosmic appreciation complete unto itself, asking for nothing more than the quiet acceptance of what exists. 40 light years from home, under an alien sun, dreaming of worlds.